Honorable guests, respected faculties, participants, and my dear friends, Namaskar, and a very good morning to everyone present here. I, Shubhanki Padi, Research Scholar, Department of Food Process Engineering, NIT Rourkela, feel privileged to welcome you all on behalf of Organizing Committee to the inaugural session of Global Initiative of Academic Records 2025 course on Microbial Decontamination through Emerging Technologies for Ensuring Food Safety and Quality, sponsored by Ministry of Education, Government of India. I now request our Director, Sir, Professor K. Umamaheshwar Rao, Sir, our Chief Guest, Professor V. M. Balasubramaniam, Sir, the Ohio State University, USA, Dr. Sabyasachi Mishra, Sir, Head of the Department, Food Process Engineering, NIT Rourkela, Dr. Sushil Kumar Sahu, Sir, GIAN Coordinator, NIT Rourkela, Dr. Rachna Sherawat, Ma'am, Coordinator, GIAN, Department of Food Process Engineering, NIT Rourkela, and Dr. Muhammad Khalid Gul, Sir, Coordinator, GIAN, Department of Food Process Engineering, NIT Rourkela, to kindly occupy the chairs on the dais. Please, sir. Thank you, everyone. I now request our student volunteers to welcome the dignitaries on the dais with bouquet. You can go and give go. Thank you. Let us begin our celebration by seeking blessings from the Almighty. Light is a symbol of brightness and prosperity. To make this day a blessed one, I would like to request the dignitaries on the dais to do the honor by lighting the lamp. Thank you. The food industry is evolving to meet the needs of health conscious consumers who desire safer, healthier, and minimally processed food devoid of synthetic additives. This course will offer an overview of food process design and the validation of various technologies aimed at ensuring food safety and minimizing nutrient loss. To brief about the course and welcome you all to this 5-day GIAN course, I request Dr. Rachna Sherawat ma'am, coordinator of this GIAN course, to deliver the welcome address. Please, ma'am.
Respected Director Sir, NIT Rourkela, esteemed foreign expert, faculty members, my faculty colleagues on the dais and off the dais, research scholars, staff members, dear students, and all the participants of the course, a very pleasant good morning to one and all present over here. I, Dr. Rachna Sherawat, Assistant Professor, Department of Food Process Engineering and Coordinator of the event, take this opportunity to extend the heartful and gratifying welcome to all of you to the 5 days workshop on the course Microbial Decontamination through Emerging Technologies for Ensuring Food Safety and Quality. First and foremost, I am deeply honored to welcome our respected Director Sir, Professor K. Uma Maheshwar Rao Sir, to this inaugural event. Sir, your presence today, despite your busy schedule, we are sincerely thankful to you for coming over here on a short notice. And we know that you have been to another program in the morning and still you are here. Thank you so much, sir. Your vibrant and dynamic leadership inspire us to strive for excellence every single day. A very warm welcome to you, sir. I extend my warm welcome to Professor Shishir Sahu, sir, our local GIAN coordinator. I welcome you, sir. I extend my welcome to Professor Sabyasachi Mishra, sir, Head of Department, Food Process Engineering. I sincerely thank you, sir, for your constant support and for permitting for the organization of this important event and which brings together the participants from different arena of the country. I welcome you, sir. It's indeed a great pleasure to welcome our expert, Professor V.M. Balasubramaniam from Ohio University, US. So we are honored to have you lead this technical session for the next 5 days of the GIAN course. Your expertise and pioneering work in the field of food quality and safety will undoubtedly be an asset to all the participants. I welcome you, sir. I would also like to welcome our course coordinator, Dr. Khalid Gul, who has been a pillar of support from the inception of the course idea to proposal drafting and now its execution. Thank you, sir, for your dedication and collaboration. I welcome you, sir. My warm welcome goes to all the faculty members of the department, and I will feel very privileged to be working with such knowledgeable and supportive colleagues. Apart from the academic excellence, our faculty contribute significantly to the administrative development and other activities of the institute. Like we have Mishra sir, who is a very important part of CSAP also, Professor Pradhan sir, Associate Dean, Professor Madhuresh, who oversees transportation, Dr. Khalid, Dr. Dibya, Dr. Vinny Rautre, who has been a very actively part of the SAC members, and Professor Arun Prasad, who is a vibrant in charge of the NCC. Many of our faculty colleagues like Dr. Chandrakant, Dr. Vivek, and Shubham, and Pritam sir, they have been part of the many central committee like IPIC, FTBI, Curriculum Committee, and many other activities. Your support has been instrumental in making this event a reality. I welcome all the faculty members of the department and other department faculty. I would like to express my sincere thanks to GIAN, Ministry of Education, Government of India for providing the financial support that made this event possible. I also extend my warm welcome to all the faculty members from various departments of NIT. And especially, I would like to welcome all the participants, those who have come from different institutions across the country. We are having 30 participants from the outside, and they belong to different states of India. And I assure you, my dear student, that these upcoming 5 days will be filled with valuable learning and technical insights and scientific discussion that will broaden your understanding of food safety and quality. The focus of this course is microbial decontamination through emerging technology, which is very highly relevant and evolving area in food processing. There are various traditional thermal processing methods that are very effective in ensuring the safety of the food, but nowadays the time and the scenario is that we have to focus more on the quality also, because the consumers are very health conscious and they want to consume the food which are minimally processed and healthy for them. Though I will not delve much into the course, as we have our course coordinator Balasubramaniam sir from Ohio University, who will give more insight about the course. I hope this course will spark curiosity, promote innovation, and enhance your understanding about thermal and non-thermal processing. You will also have the opportunity to gain hands-on experience on several of these technologies during the course. Once again, I sincerely welcome each and every one of you. Thank you for being part of this special occasion. Without your presence and participation, this event would not have been possible. Thank you all.
Thank you, ma'am. Now, I would like to request Dr. Sabyasachi Mishra sir, Head of the Department of Food Process Engineering, NIT Rourkela, to address the gathering. Please, sir.
Good morning, everyone. Our Director, Professor Ubamaheshwar Rao, our guest faculty from foreign Ohio University, Professor B.M. Balasubramaniam, GIAN Coordinator, Professor Shishir Sahu, and the Program Coordinator, Rachna and Khalid, my fellow faculty members, colleagues, dear students, and faculty members from other departments also. This is a very good opportunity to interact with you. We have been a young department. We started our journey from 2013-14, and since then we have been working hard. So far I am really happy to give you some information regarding the department. Sir, we are running BTech, MTech and PhD in food process engineering, and currently we have 15 faculty members and almost 60 plus PhD students are enrolled, out of which already 20 people have already graduated PhD student. In this last 10 to 12 years, we have been able to publish almost 950 SCI journal publication, and out of that 85 in last one academic year, and from that 40 SCI publication which are in Q1, which are considered Q1 journals, sir, out of that. And all my faculty members, as Rachna was mentioning, almost 75 to 80% of our faculty members are in the deputation to central deputation, helping the central administration in different capacity in SAC, hostel and many other things, sir, in different committees also. And in last 2 years, we have been able to conduct 2 GIAN courses, one Spark program, and this is the third GIAN course for this particular year. And recently we got 2 MSME workshop funding for training different participants. In the meantime, we got funding from FICCI for almost we trained 300 plus participants from Jharkhand, Odisha and West Bengal. Professor Madhuresh Dwivedi and Ramchandra Pradhan and Chandrakant, they played a very big role in that. And Professor Balasubramaniam has been our inspiration from the beginning, sir. Professor Divyakant said visited your lab as a Fulbright fellow, and you are the chief editor of Journal of Food Process Engineering, where almost all our faculty members act as reviewer for that particular journal. It's a great opportunity to host you in this particular. I was just discussing with you just before the meeting started. Sir is moving to University of Georgia very soon. Yeah, it was a tight packed program for him, but despite of all his busyness, he agreed to come because he committed for this GIAN course. Thank you, sir, for coming to this institute. And with this, it's a great opportunity to have this particular program for any student outside of this institute and also our students. Microbial decontamination, coming to this particular topic, let me tell you, I don't know how many of you are aware of it. Almost 38 trillion microbes are inside our body, sir, which is more than the number of cells in a human body. and still we are talking about the decontamination of microbes. Why it is so? Because all these microbes that we are talking about, they are in like have a very good symbiotic relationship with our body, mostly in our digestive system. And always, like you must have heard, we have two brains, one here and another in our digestive system. If you are hungry, you have not fed properly, probably you cannot concentrate on your work. So that's how it affects your day-to-day activity also. So it's very important. All these microorganisms that are present inside our body, they are having all kind of good things. They are the good bacteria or good whatever microorganisms that we have. So anything out of that, we talk lot about dahi, kefir and many other probiotic products. These are additional things, but what actually happens, whenever we are taking those probiotic foods and everything, all these microorganisms, when they pass through our digestive system, particularly in stomach, it's so acidic that it also kills most of the microorganism. Whatever remaining, all these 38 trillion microorganisms, they will kill the remaining microorganisms. So we already have a decontamination system inside our body. What is more important is the microorganism that is outside of our body, who actually influences all our system. You are infected with a virus, you get influenza and many other diseases. So we have to take care of that. And when it comes to food, even the curd that we are eating every day, if it is kept for 2-3 days and there is too much of microorganism activities, if you take that curd also, immediately you will fall sick. Sometimes we get that complaint from the hostel also, sir. So all these bread, dahi, all these fermented products that we get at some point of time, we have to be careful and we have to stick to the expiry date. Always, every food has an expiry date, right? Best before day. And sometimes we ignore that. Sometimes there are some adulteration at shopkeeper level. So being food process engineering person, it is our responsibility to contribute to the society that we have inside our institute. We have almost 8,500 students who are staying inside campus. Apart from that, 425 faculty members and their family members. There are 600 plus non-teaching staffs. And then PhD students and many more. So it's a mini village inside NIT Rourkela. And we being food process engineer, I think we have a bigger responsibility towards upkeeping of the safety and security of the food that we are eating inside the campus. With this and with the commitment to contribute more to the department and the institute, sir, I take this opportunity for thanking you. You have assured for our department and the things have started flowing. Recently you got a communication to give our requirements. Last meeting you promised that one. Yeah. So thank you so much, and we hope and I hope all the participants, those who have come from outside of the institute, you will have a very good stay in the campus for next 5 days and you will learn a lot of things from Professor Balasubramaniam. It's a big opportunity for me also to hear him. So I hope you will also enjoy the proceeding of this particular program. Thank you, sir.
Thank you, sir. Now I request Dr. Sushi Kumar Sahu, sir, GIAN Coordinator, NIT Rourkela, to address the gathering. Please, sir.
A very good morning to all and welcome to the GIAN course, Microbial Decontamination through Emerging Technologies to Ensure Food Safety and Quality. Respected Director, NIT Rourkela, the foreign expert of the GIAN course, Professor Balasubramaniam, Head of Department, Food Process Engineering, Course Coordinator, Rachana Sarawat, and Professor Mohammad Khalid Gul, dear faculty colleagues, participants, students, ladies and gentlemen. GIAN is a program of the Ministry of Education designed to tap the talent pool of scientists and entrepreneurs internationally to encourage their engagement within the institutes of higher education in India, to augment the country's existing academic resources, accelerate the pace of quality reform, and elevate India's scientific and technological capacity to global excellence. This course enables institutes of higher education in India to invite and host internationally renowned academicians and researchers, facilitating the co-teaching of advanced courses to Indian students and fostering collaborative relationship with experts from around the world. GIAN also offers international experts a unique opportunity to familiarize themselves with India's academic environment by interacting with local students and faculty, which can explore potential collaborations, share their expertise, and contribute to the advancement knowledge across diverse fields. So this is a very practical course, and in fact I thanks the foreign expert for traveling a long distance and coming over to Rourkela. I also thanks food engineering department to conduct so many courses in the last 1-2 years. So though we are concerned with decontamination, contamination, so like in the COVID period, everybody put a spray fast to touch anything, so to avoid get fungal infection. So similarly, food is available plenty now, Zomato, Swiggy, all those things are coming, but the packing is important, the touching is important. So the food safety, so ensuring food safety and quality is very important, and the lot of technology is behind that one. Lot of development is occurring every day. So the professor will emphasize on the modern technology involving food safety and quality, even in the name of a lot of people use washing, etc., and to get the before cooking also. So that has to be done. So a lot of things of development are taking place. So all those things will be discussed by the foreign expert. So there are we conducted already 14 GIAN courses. Another 1 or 2 courses are still left in this season, and it is going to come out. Actually, everybody is waiting for a lot of faculty is asking me about the reopening, applying of GIAN courses. It is to be opened by IIT Hyderabad. It is to be opened by IIT Hyderabad. It is to be opened by IIT Hyderabad only. So then only we can do that. So all best wishes for the course. Thank you very much.
Thank you, sir. Dr. V.M. Balasubramaniam is a professor of food engineering at the Ohio State University with joint appointments in food science and technology and food agricultural and biological science engineering. He earned his PhD in agricultural engineering from the Ohio State University in 1993. His expertise lies in minimal food manufacturing technologies, focusing on non-thermal and thermal processing techniques to enhance food safety and quality. Dr. Subramaniam's impactful career includes prior research roles at the Illinois Institute of Technology. He is a highly recognized leader, evidenced by numerous accolades such as the 2021 IFT Research and Development Award, the 2018 OSU CFAES Innovator of the Year Award, and the fellowships in prestigious organizations like IFT, IUFOST, and ISAE. He serves as Editor-in-Chief of the Journal of Food Process Engineering. With over 132 peer-reviewed publications and a strong record of mentorship, Dr. Balasubramaniam has significantly advanced the field of food engineering and continues to contribute through research, teaching, and extensive professional service. We are overwhelmed to have you here with us today. Now, I request Professor V.M. Balasubramaniam, sir, to please address the gathering.
Good morning, everyone. First of all, I would like to thank the NIT Rourkela for inviting me here. It's very nice opportunity to meet all of you. Particularly, I would like to thank the director, Dr. Rao, the GIAN coordinator, Dr. Shagu, and also the head of the department, Dr. Mishra, and then the course convener, Dr. Sharwad, and Dr. Khalid Kul, for making all the arrangements. especially with the travel and other things. I think there's a lot of things went behind the scenes, and I appreciate that. So the food processing is near and dear to my heart, and I think already we have a lot of things kind of summarized why food processing and engineering is important. I think over the next 50 years, the global population is going to increase, and we have as the food science and engineering faculty, we have the responsibility to feed the safe and nutritious food to all these growing population. At the same time, the consumers also more and more interested in healthy processed food, because they are skeptical about various preservatives and chemicals added to the processed food, and they worry that particularly in Western countries, processed food is not healthy. So we as a food scientists and engineers have the responsibility to develop next generation of food processing and manufacturing technologies that meets their expectation. Looking in another dimension, we are also increasingly interested in sustainability of food processing or the environment, how those affects. If you look at globally of various processing industries, food processing is probably among the top polluter in terms of various emissions. So there is a need to develop technologies that reduce the emission, but at the same time reduce the energy use, water use, and reduce food waste, so that we can able to make minimal impact on the environment. So as a result, you can see that food processing is not just a single focus, it's a multi-dimensional. It has a dimensions in ensuring food safety. It has an emphasis on ensuring health and wellness of the global population. At the same time, it has an impact on the sustainability of the environment. So in the next 5 days, I look forward to learn along with you some of the developments happening in the food processing, and how do we develop and design and validate novel technologies that meets the consumer expectations. Thank you.
Thank you, sir. I now request our director, sir, Professor K. Uma Maheshwar Rao, sir, NIT Rourkela, to address the gathering. Please, sir.
Thank you very much. And then the most distinguished dignitaries on the dais, Professor Balasubramaniam, Professor of Food Engineering, Ohio State University, now shortly shifting to Georgia Institute of Technology, and Professor Sabyasachi Mishra, Head of the Department, and Professor Rachna Sharawat Madam, Assistant Professor, and then convener of this program, and then co-convener Muhammad Khalid Gul, and my faculty members from food processing, mechanical, and then guest house and metallurgy, and the various other departments, and my dearest faculty members. I'm really extremely happy to be present here this morning before you for the inauguration of the GIAN program. Just about a couple of days ago only, I was talking to my office that this year over, that I have not been really inaugurating any GIAN programs. Right, so no, it's like we always start the program with lighting the lamp, Tamasoma Jyotirgamaya, from ignorance to awareness. That itself is the ethics or the motto of the GIAN program, from ignorance to knowledge or awareness. So now at least I'm happy that I know, I have been seeing for the last 3+ years that NIT Rourkela is one of the institutions which is offering more GIAN programs. Okay, and this is a greatest opportunity for my youngest, the students, that to interact with a person like what we have today is Professor Bala, because he just told me that he is comfortable being called as Professor Bala. Right. So now I'm also comfortable. So now, and as far as this particular topic is concerned, decontamination through emerging technologies for food safety. I have really precisely stated. I can see it here. So now, this is a very big debatable topic here. The debate is that it is on its own a conflicting topic also. Just now, Professor Sabyasachi has really very emphatically stated that the human body is a biochemical factory. Right? It's a huge biochemical factory wherein something around more than 35 trillion microbes are residing in the system. Okay, and he spoke about a curd. Curd is one thing which is essential last. It's like singing the national anthem. It's like that in South India, right? That I have not seen in Odisha also. But then he is really claiming that curd is good. Okay, but then never ever curd is served right in Odisha or Bengal or northern part of it. But then in South it is served. Without curd, the food is not complete. Okay. The paradox here I just would like to tell is that any meeting and every meeting, if I go tomorrow to food processing department, I am 100% sure that Professor Sabyasachi will give me a samosa and jalebi. यहीं पर हम मार खाया। अभी सर ने कहा है कि right, these are all the foods which are really contaminating our gut. ठीक है ना? तो फिर यहाँ खड़ा होकर के कहेंगे कुछ, वहाँ पर बैठे करेंगे कुछ. हम innocent people like us, right? We are minors, not MINOR. Minor means जो खदान में जाते हैं, right, अंदर, right? ज्ञान प्राप्त करने के लिए नहीं, लोहा बाहर निकालने के लिए. अपने ज्ञान पे हम आधार है. Right? You preach us something that it is a biochemical factory, and then you speak about all that one. But then today the paradox, another paradox here is that on a daily basis, अगर मैं head of this institution के नाते मेन गेट पे अगर कुर्सी लगा के बैठूं, जोमेटो कितने बार आता है कैंपस के अंदर? And Professor Mishra also has stated, I have just really written down because you have used very beautiful sentences. Today the consumer is conscious of health. Is he? Is he conscious of health? If he is conscious of health, okay, why Zomato has now become such a popular company who have come on campus for recruitment paying the highest? It is absolutely a food delivery company. ठीक है ना? Food delivery company यहाँ तक कि आपको पता भी नहीं है उस बक्सा में जो खाना है, are you conscious of that particular food, of what exactly is that quality of food? नहीं ना? There was a long discussion, because these are all some things which I am really put to, a long discussion and debate, and then students wanted pizza, Domino's pizza on campus. एक बार मना किया तो दोबारा आता है, दोबारा मना कर तीसरी बार आता है. ऐसी वो तो ये विक्रमा और वेताल की तरह वो इससे बार बार आ रहा. मैंने सोचा ठीक है चलो यार, अप्रूवल ही दे ही देते हैं. डोमिनो पिज्जा आ गया. Are all these foods good for your well-being? हमें पता नहीं. Right? So now the question which I just would like to know is that I am from a small town near Hyderabad, and लोएस्ट मिडिल क्लास फैमिली से आया हूँ मैं. ठीक है ना? इसका ताल्लुक यहाँ पर क्या है आप सोच सकते हैं. यही है कि my mother used to always have rice cooked more than what we consume that night. Okay? And she always used to, because our school starts at 9:30. We have to really walk around 5 kilometers to reach our school, or cycle. After my father purchased a cycle, my brother used to put me there on cycle. So, but our religiously the breakfast used to be पानी में भिगा हुआ खल का राइस added with some bit of curd, right? और कुछ नहीं, और बिल्कुल कुछ नहीं, right? पेट भी अपने जगह पे बहुत मस्त रहता था, ना कोई प्रॉब्लम, ना कोई झमेला, ना झंझट, राइट? डायरिया डिसेंट्री का बात ही नहीं होता था, ठीक है? वहाँ से शुरू किया मेरा इस जर्नी को, इस बॉडी लेकर के. देन आई जॉइंड द हॉस्टल. एवरी वीकेंड I suffered amoebiasis and then diarrhea, and once I was even hospitalized because of the uncontrolled diarrhea. ठीक है? The contamination has been from my childhood in the food. Okay? Contamination has become the order today by many suppliers. यहाँ तक कि दूध, यहाँ राउरकेला में, I've been struggling. Rajesh knows if he still remembers that. The दूध में, खड़गपुर में, was more than 36 years I was in Kharagpur. The only thing which I personally like is to take uncontaminated. Decontamination अलग बात है. पहले हम कंटामिनेट करेंगे, इसके बाद डिकंटामिनेट करेंगे, वो दूसरी चर्चा है, वो ज्ञान के लिए चाहिए. लेकिन पहला कदम में कंटामिनेट क्यों करना है, ताकि हम उससे नौबत ले पड़े. वाई शुड वी रियली अलाउ कंटामिनेशन? हल्दी कंटामिनेटेड, राइट? टुडे हल्दी इज कंटामिनेटेड, और वॉट एवर द मसाला दैट वी रियली पुट इज कंटामिनेटेड. दूध कंटामिनेटेड. You buy anything, it's contaminated food. पिछले 3 से प्लस साल से मैं 1 लीटर दूध बिना कंटामिनेटेड वाला मैं खोज रहा हूं. सही में, भगवान कसम, राइट? वो दूध नहीं मिल रहा है. हल्दी, स्ट्रॉन्ग, पंजेंट, येलो एंड मिर्च, These are all that. यहाँ तक कि सब बाहर से अपना कौन सा मार्केट है बहुत फेमस है यार, आम बगान से कोई ग्रीन खरीद लीजिएगा, and then you dip it in water, you get green color out of that one. When food has become a business, we have allowed contamination into that, because people are now looking at make money and make people sick, so that multiple companies or multiple entrepreneurs, FTBI, will register from that. First you contaminate. Okay, go to Subrat Panda. I have an idea in my brain to decontaminate that. So these are some questions which we need to. What has been wrong with Indian system that we adopted? Burgers, bagels, pizzas. What was wrong with our Indian system? हंडी में दही जमा करता था, कोई खराबी नहीं था. But why have you really adopted, allowed and accepted and been the mouthpiece of promoting this Western food, which is, the moment Professor Bala told that he is from Georgia, from Kharagpur, I went to Georgia Institute of Technology for some official purpose only. My brother, still now, my cousin is not my own brother. My cousin, he still lives in Georgia, sir, at that area. When I went to his house, his wife is also employee and my brother is also employee. And then उन्होंने कहा कि फ्रिज में खाना है, थोड़ा उसको माइक्रोवेव में गर्म करके खाना है. जैसे मैंने खोला, जैसे बैंगन का जैसे मसाला बैंगन बनाया था, जैसे मैंने वो प्लास्टिक का ढक्कन खोला, बहुत ऑफेंसिव स्मेल आया, बहुत ही ऑफेंसिव स्मेल आया. नहीं, I just immediately called my brother. This seems to be completely decomposed, fermented. No, you to just about a month ago. He said that this is fresh, just prepared a month ago. तब से लगा कि we are not, Indians are not cursed. At least we take a week ago food, keeping it in fridge. And then our clean carpet, they try to use fridge a lot, try to give us a week or 10 days old, but then not months ago. This is a biggest question, my dear boys and girls here. If you don't understand this factory, completely, and start killing the microbes which are really giving you the strength, and then try to take a bacillus or whatever the type of artificial, the bacteria into that one. Is it correct? I take pizza, I take samosa, I take jalebi, I used to like a lot. Oh, kya, chana poda. The only sweet which I used to like in Bhubanesh, or rather Rourkela campus, which whenever I used to go to guest house for food, is that was the only thing, though it is repeated in n number of times, that is only one thing which I really liked. Right? So now, even that also I had to stop. The reason is that your blood sugar levels go up, spike. Right? And so much so that I entered NIT Rourkela, BP control में, sugar control में, and cholesterol control में था. I used to be taking pride of myself that this little body, 5 feet 4.5 inches, is not contaminated to decontaminated. 3 साल में sugar is not getting controlled. 2 बार ले रहा हूँ दवाई, मॉर्निंग एक, रात को एक. कंट्रोल नहीं हो रहा है प्रोफेसर बाला. मैं आपसे एक रिक्वेस्ट कर रहा हूँ. और मुझे माइग्रेन है, मुझे वर्टिगो भी है, ये बहुत पहले से ही है. लेकिन बीपी भी it starts playing havoc with me. I pop in so many medicines for controlling BP. मॉर्निंग 1, लंच के बाद 1, रात को 1, 3 फॉर बीपी, 2 दवाई फॉर शुगर. होता क्या है? And when I am taking so many chemicals into my body, 38 trillion gaya. All the 38 trillion are gone. And then बहुत सारे, I experience a lot of pain. And then immediately I used to have the most dependable and reliable doctor, सौम्य रंजन बेहरा. मैं फ़ोन करके बताता हूँ, डॉक्टर सौम्या मुझे ये दर्द हो रहा है. इमीडिएटली पेन किलर, इसके पीछे पेंटाप्रोजोल 40. एंड मैं कहता हूँ कि ये सब देने से जब पेट में दर्द रहता ही जाता है, तो लैक्टोबैसिलस 1. तो मैं, क्वेश्चन इज दैट माय डोमेस्टिक हेल्प, शी इज़ ए वेरी इनोसेंट गर्ल, शी इज़ फ्रॉम मुंडा ट्राइब. शी टोल्ड मी दैट why take this type of faltu khana, why take that so many medicines, 6 tablets a morning. And then she has introduced me to pakhal bath. And I really remember that this pakhal bath is nothing different than what my mother used to give. It is the same thing. And for the last 6 months I am taking that pakhal bath. अभी कोशिश कर रहा हूँ ये फैक्ट्री में ये डिकंटामिनेट होता है कि नहीं. Right, so now I am just only requesting my dear boys and girls here. don't celebrate your birthdays on cream laden cakes. You are abusing your own health. एक क्लास अटेंड करेंगे, जगदा गेट से बाहर जाएंगे, एक वहाँ पर एक समोसा खाएंगे, राइट, और चाय पिएंगे, आएंगे और बीच में कुछ और भी करेंगे, राइट, आएंगे फिर से. बाय द टाइम, बाय द इवनिंग, you have added so much of concentrated acids into your gut. Gut is also another brain. Rather, gut controls your main brain. This is the beauty of that one. And then we are abusing this fellow gut, left, right and center. Dumping fermented, dumping, what is that called? This contaminated, dumping unwanted foods. And then शाम तक आप एकदम, you are becoming absolutely a zombie walking. कहाँ जा रहे हो, क्यों जा रहे हो, बिल्कुल पता भी नहीं है, जा रहे हो, जाते रहो. Please try to be aware. Last closing sentence is that it's a beautiful opportunity to be living consciously. I'm using the word again. Living consciously. कोई ज़बरदस्ती नहीं है आपको for making any decision or anything unconsciously or by compulsion. Right? जीने के लिए, इस धरती पे आने के लिए कोई जेई का जरूरत नहीं था. Right? You have never, or your parents have never cleared JET for you to give life on this earth. To be living in ecstasy, I use the same sentence in the morning. To be living in ecstasy, right? Becoming a part of your life, you don't have to qualify in any examination. You don't have to maintain any CGPA. This is the beauty of life. Live to its fullest extent, consciously, not by compulsion. Professor Sabyasachi मुझे बुलाया, please address my faculty. जाने के बाद वहाँ पर प्लेट पे फ्राइड काजू एंड एक समोसा, एक कचौड़ी और एक चना पोड़ा, ये सब रखेंगे. Whether to take that or not to take that one should be my choice. Thank you very much. Right? And then I wish you all, I wish you all that Indian system was not never ever wrong. Right? We are not here to promote a foreign industry. The very first question which I don't really understand is that why Kentucky chicken should become such a popular thing. Why Domino's pizza should become such a popular. Why there is no Zomato supplying Pakal Bhat. Ask this question. Thank you.
Thank you so much, sir. Now, I would like to request our director, sir, to present the token of appreciation to our foreign guest faculty, Professor V.M. Balasubramaniam, sir.
I wish to visit us regularly and as a visiting faculty.
Now, I would like to request Dr. Sabyasachi, sir, to present the token of appreciation to Director Professor K. Uma Maheshwar Rao, sir. Now, I request Dr. Sabyasachi Mishra, sir, to present the token of appreciation to Dr. Sushir Kumar Sahu, sir. Now, I would like to request Dr. Rachna ma'am to present the token of appreciation to Dr. Sabsachi Mishra sir. N- Now, I would like to request Director sir to present the token of appreciation to Dr. Rachna Sherawat ma'am. Now, I would like to request Dr. Sishir sir to present the token of appreciation to Dr. Khalid Gul sir. Thank you, everyone. We have come to the end of the inaugural session, so I would like to request Dr. Khalid Gul sir, coordinator of this GIAN course, to propose the vote of thanks.
Professor V.M. Balasubramaniam, our guest from the Ohio State University. Professor K. Umamaheshwar Rao sir, Honorable Director, NIT Rourkela and patron of this GIAN course. Professor Shishir Kumar Sahu, Local Coordinator for GIAN NIT Rourkela. Professor Sabsachi Mishra, Head of the Department Food Process Engineering. My colleague and convener of this program, Professor Rachna Sherawat. My faculty colleagues from the Department of Food Process Engineering and other faculty members. Dear students who have joined us today, a very good morning to all of you, and thank you so much for joining us today for the inaugural session. First and foremost, I would like to thank our foreign expert, Professor V.M. Balasubramaniam, for taking time and kindly agreeing to be our host for the next, for this week, and be the guest speaker for this GIAN course. Thank you so much, sir, for coming over to NIT Rourkela. We are really pleased to have you on the campus. I would like to take this opportunity to thank our leader, Director NIT Rourkela, Professor K. Umamaheshwar Rao sir, for his dynamic vision and his support in for extending support to not just this GIAN course, for every program that we are organizing in our department. Thank you so much, sir. Next, I would like to thank our head of the department, Professor Sabsachi Mishra sir, for his support and vision and dedication and passion that makes us go through every day. And thank you so much, sir, for your kind insights while we designed this course and also throughout the process till today. Next, I would also like to thank Professor Shishir Sahu sir, the local GIAN coordinator, for extending his help right from the inception of this course to the time when we filled up applications for this course, and finally when we got the course from IIT Hyderabad. I would like to extend thanks to Ministry of Education for financially supporting us so that we could organize this course on the campus. Simultaneously, I would also like to thank GIAN National Coordinator, which is hosted by IIT Hyderabad, for giving us this opportunity to host this GIAN course on the campus. I would also like to thank my colleague, Professor Rachna Sherawat, for being really dedicated, passionate, and really hardworking. She has had a lot of sleepless nights while designing this course and making arrangements for Professor Bala also. Thank you so much, ma'am. So it would be really if I do not it will be really sad if I don't mention my faculty colleagues who have been with us and extended every possible help throughout the journey. Also, my faculty colleagues from other departments who have joined us today, Head of the Unit for Safety and Security for extending every possible help, Chief Warden's Office for extending help in making the stay of the students comfortable. We have students coming from as far from Assam universities and then Central University Pondicherry also. Thank you so much for joining us, and I would really hope that at the end of this course you will get a lot of insights about the course, and also you will take a lot of memories from the campus and make friends and collaborations from different faculty members, not just in our department but other departments also. Also, I would like to thank the faculty members and students of our department who have been with us in the past week, and also who will be with us in this week and extending support to us, and all the officers of university of this institute and Angtel in particularly. Thank you so much for your kind support. Thank you so much. With this, we come to the end of the inaugural session. Thank you so much.
Thank you, everyone. Once again, a very thank you to for joining with us. Have a good day. We have a high tea arranged outside. Please join us for that. Thank you.
No, nothing. Yeah, now it's coming.
We can write here also.
Right, sure. Yeah, right, yeah.
Went out from
Mhm.
Sir, no.
Right, okay, sure, yeah.
wetness is in this side.
Right, yeah, sure. Hmm.
Yes.
Yeah, right, sure, right.
कल का 9 o'clock है तो 8:45 everyone should be here. They can have some informal discussion also.
Hello, hello, hello.
Front bench.
Okay. Okay. Good afternoon, everyone. So, in this lecture, I'm going to primarily talk about some brief introduction about food processing. So, I think a class like this normally have people with different backgrounds, and some probably take engineering classes, some take microbiology, some come from traditional chemistry or other fields. So, because food science and engineering attracts people with a diverse background, so that's where I think introduction is always helpful. And food science and technology is a multidisciplinary field. So that means you need to know the engineering, you need to know the chemistry, you need to know the microbiology. You also probably need to know the various other things, like for example, some aspects of business if you are working in the industry, because you are making product, but if you are not selling them, if you are not selling them in an economical way, it's not going to be viable, commercially viable. So you have to kind of familiar with that. So today, I think we also look at, when you look at some of the processing technologies, in addition to some of these fields, you have to look at the nutrition and health, because traditionally food processing is validated based on microbiological safety, but more and more the consumers are interested in health and wellness. So there is an interest to see how much nutrients are preserved by different technologies, so you can able to choose the one which preserve the nutrients better compared to the other one. Now, if you look at the consumers, they normally very much interested in sustainability. At least a lot of statements I make is based on the US consumers, but that may be true for Indian consumers as well, but we can discuss that during the discussion session later on. But when I look at sustainability, a lot of consumers want sustainable product, but when you ask how much they're willing to pay, are they willing to pay additional premium for the sustainable effort, usually they do not want to do that. So they still want to have economical, affordable product. So it's kind of, they expect the food processor to take care of the sustainable effort, but nevertheless, they want something affordable. Consumer acceptance is also very important when you look at the some of these technologies. Again, in the US, if you look at food radiation, it has been mentioned many times that it is scientifically very safe and commercially viable technology. However, today, this is something have been proven in the 1950s and 60s, but even today the radiation is not commercially available. Part of the reason is that consumers associate with radiation with the nuclear war, and they kind of worried consuming some radioactive product, even though scientifically shown the food are not radioactive, like after treating with radiation. So consumer acceptance is very important. The supply chain is also very important, because especially when you are processing new technology products, the vendor may not have the proper supply chain, so that affect. And we have seen the supply chain effects during COVID, because with the COVID, a lot of the supply chain and manufacturing, everything is get upset, and as a result, I think a lot of changes probably happen. So when you develop a technology, just because you are an engineer, you have a very good idea, do not expect that to be commercially successful. You need to be able to make sure your broader knowledge is important, so that you can able to make it a viable technology. If you follow social media and then also food processing, you probably hear a lot of things, particularly about food processing. People say food processing is bad. I think processed food, ultra processed food is evil and all those type of things. While there may be an element of truth to it, but I think the ordinary consumer probably do not understand what causing the processed food become unhealthy. So if you look at processed food, you have two things. One is processing. That means it can go through a heat treatment, it can go through a pressure treatment, electric field treatment. So it's a process side. The second thing is formulation or product development. So when you product develop, you may be adding a lot of synthetic ingredients, and some of those ingredients probably cause the adverse effect, especially some of these ingredients may not be properly tested, and if that ingredients are not properly tested, so they may provide certain functionality, for example adding certain flavor, but it may have some side effect on your gut microflora, and that's where the people get sick and feeling and so on. But a lay consumer probably do not understand what is the difference between adding ingredients versus processing, and they think that summarily reject processing as the evil for all those things. Now I think later part of this class we will also talk about some of the new processing technologies. So when you look at thermal processing, while it is traditionally make the food safe, it also degrade quality, it also degrade flavor and the many other product attributes. So I think the newer processing technologies have minimal processing technologies. In other words, they minimize the thermal exposure, they can able to preserve the quality attributes while making the food safe. So we'll kind of talk about some of those things. But other than that, I think food processing has numerous benefits, including increase in diversity, safety, convenience, flavor, texture, like I think fortification enrichment, like for example, when you look at rice, you can probably fortify rice with number of nutrients, so that it may not be otherwise possible. You have milk, you may be fortified with certain vitamins, so that it can kind of provide certain benefits and so on. And so I think overall, processing technology has a number of benefits, but as a food science and engineering community, we have done poor job in communicating the benefits of food processing. So that's where you have a lot of the negative commentary comes in. And if you look at it one way, all of us are living in the globe, we are all consumers, and we consume at least 3 meals a day, most of us. And so that means the food science and engineering contributions there to take that raw product, convert them into value added product and bring them to the table. So I think in that sense, food engineers, food scientists play a key role in terms of creating that value added processing. But if you ask a lay consumer, they may not know who is food engineer is or who is a food scientist is. They primarily know farmer, or they may know the end side, but they may not know somewhere in between. There's a scientific communities there. So that's something, as some of you get into the academic and you may want to communicate to the public the importance of some of these processing methods. Now I think the next couple of slides I'm going to try to quickly go through some basic concepts. So if you already have these basic concepts, it's a review, or you may be sitting here and teaching this, or some of you probably new, so you may kind of learn. One of the key thing is mass balance, because in food processing you are taking raw product and then convert them into value added product. A simple example is, like for example, you take some orange fruit, you kind of remove the peel and then you extract the juice, and then you have the final product. And if you look at the mass, you still have that mass balance probably going to come in. So you have say 1000 kilograms of orange fruit is there, and then maybe 60% of fruit is peeled and skin and everything, and then maybe you have 30-40% of juice comes out. So that's a simple mass balance. This mass balance help you to understand what is going inside your processing equipment, what's coming out, what is wasted, and the idea here is, how do I reuse some of this waste so that I can minimize the waste, because in the past, wastage in food processing is not something big concern, whereas now I think there's more and more efforts on valorization. I think they want to, how do you minimize the waste by getting some of the ingredients. So for example, if you are processing some tomato juice, you extract the juice and you throw away the pomace, but the tomato skin, the pulp, the pomace has a lot of what they call nutrients in there, and those lycopene and other ingredients may be extracted from the skin that can provide a value added type product. So having a sense of mass balance always help you to understand, and whether you do in a small lab scale with a 5 gram, 10 gram of sample, or you do it in a 1 ton type of industrial sample, mass balance always helpful to have. Energy balance, again, with today's interest in sustainability, the goal is to minimize the energy use, but food processing use variety of energy sources. Traditionally, a lot of the foods are heat processed, so you may be doing blanching, you may be doing pasteurization, you may be doing commercial sterilization, or some of the new processing methods using high pressure or radiation. So these are all different forms of energy sources, and part of those energy is going to modify the food, kill the bacteria, and you kind of make the food palatable. So when you pasteurize or sterilize, the same thing happens when you do radiation or high pressure processing or pulse electric field processing. So again, here you have to look at how much energy you input, how much energy you gain, or what's the output, and then how much energy is wasted and so on. And you have to kind of find a way to reduce some of those energy use. So traditional sense, you probably employ a lot of pumps, heat exchangers, and many of the devices to process food. So you can probably find a way to better utilize the heat exchangers, so you can have much more efficient heat exchanging systems. You can use a better pumping efficiency so that you can reduce the energy use in some of those things. When you are using microwave or warm heating, you are using electrical energy. If you look at traditional thermal processing, you take steam and convert that steam to heat your pasteurization equipment or canning equipment. So steam is produced off-site and then transported to the processing plant. Along the way, there's a lot of energy is kind of wasted, and that's kind of oftentimes ignored. Now, on the other hand, when you have microwave or warm heating, you produce electricity, and that electricity is converted into microwave or warm heating that directly impinge on your surface and then convert into electrical energy to treat the food. So it's much more energy efficient. The same way, some of the new processing technologies like high pressure processing or pulse electric field processing use electrical systems, so they probably make things much more energy efficient. Another consideration is that when you have electrical energy systems, you can kind of take that and use many ways of producing electricity. So for example, in India we have abundance of solar power, so you can produce electricity using solar and then use one of these technologies to do processing rather than creating steam, which can have harmful emissions and things of that nature. So that's kind of again the energy balance is something important. Now, this slide just to show when you do food processing, you're probably going to have both mass balance and energy balance needs to be coupled, and they need to be considered. So, for example, you may be taking some tomato puree and maybe adding some water, mixing it, and then maybe create some type of juice type of product. You may have certain water need, energy, and then you probably have certain output. So, you have to consider along the way what you input, what you are outputting, and what's wasted, and all those things. And so, you always kind of pay attention to reduce the energy use and reduce the water use. Now, most of the foods processed today, these are heat processed or thermally processed. Even though there's a lot of excitement about novel processing technologies, these technologies are still at infancy. So, that means maybe 5 or 10% of the products are processed with the new technologies, maybe more in the future, but today most of the foods are thermally processed. So, still we need to understand the thermal processing basics so that we can able to understand them. So, one of the bigger way the heat is transferred within the food is through 3 sources of heating: conduction, convection, and radiation. So, conduction heat transfer is the heat transfer taking in solids. So, here you have molecules within the solids, they kind of agitate and then transfer heat from one molecule to other molecule. Convection heat transfer, essentially the heat transfer taking place in liquids, like for example, when you are boiling water, the heat transfer taking place is convection heat transfer. Radiation is the heat transfer taking in free space. When you are walking on a hot day today, like today, you can see you feel warmth from the sun, even though sun is away so many miles away, you still feel the heat because the heat is transferred through radiation. So, in terms of conduction heat transfer, the example is if you have a piece of potato, you are heating the potato, the heat transfer taking place within the potato is an example for conduction. So, that means you have transferring heat from the outside of the potato. Let us say the potato you put in a boiling water, the water is at 100 Celsius, the potato is at 25 degrees Celsius. So, when you drop it in the boiling water, initially it may be 25 Celsius, and then slowly the surface start warm to higher temperature, and then eventually reach 100 Celsius. Then the heat is diffusing through the interior of the product, and then eventually the whole thing is going to reach 100 Celsius. So, conduction heat transfer is size dependent. So, that means if you have a small product like pea, you can able to heat it quickly, whereas if you have a massive say some meat product or chicken, then that takes longer time to cook because the heat transfer is very long. So, if you look at some of the newer processing methods like microwave or home heating, that conduction heat transfer limitation can be overcome because microwave can heat the entire mass of the product in a single operation, so that you can able to heat the whole thing and you can minimize that temperature gradient. Because whenever there is a temperature gradient in the product, that means maybe portion of the product which already reached, it may be degrading, whereas the portion of the product still reaching the temperature may not be cooked if properly, that can be a food safety problem. So, understanding the conduction, convection and radiation heat transfer is one of the very critical thing when you are doing food safety assessment, as well as probably looking at the nutrition assessment. Again, I am just going through basics, but probably you may want to refresh if you are not familiar with some of the concepts. So, heat exchangers, these are devices where you can exchange heat from say hot steam to maybe your product which is at a different temperature. And heat exchanger can mean different things. So, for example, if you have an evaporator, you may be concentrating liquids. On the other hand, if you have a freezer, you are going to cool it down. That itself is a heat exchanger, and so that you can extend the shelf life by freezing. You have pasteurization, sterilization, ovens, fryers, microwave heaters. So, there is all different type of heat exchanger equipments are available. Now, when you are doing food processing, we are going to consider, assuming a lot of things are heat processed, there are a couple of things going to happen. One, there is something called reaction kinetics is going to take place. The second is something called transport phenomena, and then the impact of process. So, what is reaction kinetics? So, when you look at the raw product, you have a potato, you have a meat product that contains maybe a lot of nutrients, it also have a lot of microorganisms. Our goal for food processing is by heating that potato, you kill any harmful bacteria and any spoilage bacteria, while you want to retain as much as nutrient as possible without destroying. Now, chances are some nutrients are heat sensitive. So, when you are heat treating, some of those nutrients may be damaged while you are killing some of the other products. So, this is where you are going to look at the reaction kinetics you have to consider. You have to consider the microorganisms, the quality attributes, because when you are heating that potato, the potato initially very firm, then as it gains more heat, it's cooked, it has starch conversions, all those things taking place, it becoming more and more mushy. And if you look at a canned potato, it looks much more mushy because they want to ensure it's fully cooked so that all the microorganisms are dead. But it also compromises the nutrition and the textural attributes. So, this is where you have to look at the microbiological safety. The second part of it is the transport phenomena, and during cooking or heat treatment, you have to look at the heat transfer. So, for example, you have a can of peas or meat or whatever it is you are cooking, you have to see how uniformly heat is applied in your treatment. In addition to that, you also look at how uniformly heat applied inside that big vessel where it's maybe canning equipment, retard or pasteurizer or microwave sterilizer and so on. So, how uniformly temperatures are distributed. So, the treatment uniformity is very important, because a lot of the kinetic models assume your microorganisms are killed at a particular temperature for particular time. So, when you are doing an industrial scale, it's almost impossible to maintain that uniformity, but you want to develop approaches that maintain that uniformity as much as possible. You may also have mass transfer taking place. So, for example, when you are frying potato, the potato is going to absorb fat from the oil, it may give up water from the tissue. So, this can be mass transfer taking place. So, you need to understand the mass transfer as well. And then you also need to pay attention to the what they call engineering properties. A lot of times when we ask what is the engineering properties, sometimes students may erroneously tell it's the color or it may be the water activity, texture, those type of things. Those are all product attributes, but not necessarily the engineering properties I am mentioning. The engineering properties I mentioned here are the thermal conductivity, the specific heat, the density, some of those things. We will talk more about those things. These again control how uniformly the food is heated or the process is delivered, so that you can able to get that thing done. So once you establish the microbiological safety, uniformity of the process, you can establish your whole wholesome uniform process. So here we kind of went through this here, and I think this is a picture of an autoclave, just to give an example how an autoclave may look like. If I have a person standing here, the person may look very minuscule because this is much larger diameter and much larger in length, and then he may be putting several tons of product depending on the size of the retort and other things. And this slide here just to show that how your for example, the temperature distribution during microwave heating or other process being verified either by mathematical modeling or through experimental measurements. So these are some of the key engineering properties I talked about. Thermal conductivity is the ability of the material to conduct heat. So when you look at metals like steel or things like that, they can conduct heat much more quickly. When you look at the insulation materials like plastics, they conduct heat very slowly. On the other hand, if you look at food materials, they were intermediately conduct heat. So that's something we need to know. Specific heat is the amount of heat per unit mass required to raise the temperature by 1 degree Celsius. So how much energy you need to raise the temperature by heating. Density, the compactness, it's basically mass per unit volume. Thermal diffusivity, basically you take the thermal conductivity, specific heat, density, and then you kind of divide K by rho Cp. So it's kind of the unit, so how uniformly the heat is distributed during processing. You may have some liquid fluids. The viscosity can provide an idea the resistance of a fluid to deformation during flow. So when you want to pump different fluids, you can able to get this. And again, there's a whole set of field called rheology, Newtonian, non-Newtonian fluids, which I'm not going to go over here, but you need to understand so that you can able to get some of these things covered properly. When you look at some of the newer technologies, the compressibility is another parameter you look at. Like we talk about high pressure processing. High pressure processing, you are applying 600 megapascal pressure to pasteurize food. So normally when you have 1 liter volume of water, during processing it's reduced by 15%. So in other words, it's going to go from 1 liter to 0.85 liters. So there's a 15% reduction in volume taking place, and that's the compressibility. So different substances, fats, lipids, protein, different compressibility values. When you look at the electrical technologies like microwave heating or ohmic heating, the electrical conductivity property is important. So similar to thermal conductivity, it's the ability of the material to conduct electricity that's important. When you look at freezing type technologies, you need to understand the latent heat. So the latent heat, basically how much energy you need to provide or extract to require a phase change. So for example, you have water converted into ice, so that means you are going to remove certain latent heat. Or you have ice, you are adding certain heat, it converts into water, so again you are going to add certain latent heat. So what's the difference between sensible heat and latent heat? So there's two forms of heat. Sensible heat is something you can able to measure temperature change by monitoring using a thermocouple. So for example, when you take a beaker of water and then you put it in the thermometer and then you heat the water, you can see the thermometer going to show the temperature increase from 25, 50, 75 Celsius and so on. So you can see the phase change. On the other hand, you take the same beaker and then you heat until everything converts into water. When the water reaches close to 100 Celsius, the thermometer is going to stop showing any temperature change, even though heat is continuously applied. Then a lot of those energy goes into converting the phase from liquid into vapor, so that by you're going to show that as a latent heat. On the other side, when you're freezing it, that heat energy is going to convert that into ice. So again, you have to kind of consider that form of energy. Now, some of these things are engineering properties, but there are certain chemical properties also important. One is the product acidity. The acidity is very important. A lot of the foods are neutral pH, whereas you probably have certain fruits and other things are acidic. And why acidity is important? Because microorganisms, like living beings, they also do not like very acidic environment. So that means if you have a pH of less than 4.6, that generally inhibit the growth of microorganisms, whereas when the pH is above 4.6 or more close to 6 or 7, the microorganisms like it and they can thrive well. So that means your processing treatment may be different. The severity of the treatment may be needed when you have pH is close to 6 or 7, whereas the pH is less than 4.6, you can have less severe treatment is sufficient. So that's why pH is important. So when you are processing any food, you always try to understand, measure pH and water activity, because that will probably help to decide what type of treatment you need. Similarly, water activity. The water activity basically going to tell you, how much water available for certain microbial reactions or chemical reactions. And again, 0.85 was above 0.85, like raw food materials, they probably permit growth of microorganisms. Whereas when the water activity is less than 0.85, say 0.7, 0.6, you have less water available for chemical reactions or microbial reactions. And when the reaction water activity value is about 0.2, 0.1, then even more better. So that's where again you have to consider microorganisms and water activity and how they interact with pH, all those things. Normally, in the US regulations, they classify foods as a low acid food and high acid foods. So low acid means it has a low acidic content, so that means the pH is above 4.6, and then the water activity is 0.85. So many vegetables, meat products, dairy products, and it allows the growth of the Clostridium botulinum. So I mentioned pH of 4.6. What is the magic about 4.6? And I mentioned here Clostridium botulinum. So Clostridium botulinum is probably one of the deadliest spore forming bacteria. It has an effect on human brain and other things. So they can form toxin and they can cause death. So they require above 4.6 to survive and proliferate, whereas less than 4.6 they are inhibited. So that's why it's called low acid food. High acid foods, like for example, you may have juice and other products, they have pH less than 4.6, and here you can have a mild treatment. So just to give an idea, if you have a soup, generally potato soup, it's more neutral pH. You may have to, if you need to do the canning, you have to treat that maybe 121 Celsius for a longer time. Whereas if you have a tomato juice, generally the pH is less than 4.6, then acidic, you don't need to go all the way to 121 Celsius, probably somewhere 90 Celsius or 100 Celsius for a few minutes is sufficient, because it's more acidic product. So the acidity determines how intensive or less intensive the heat treatment can be. Acidified products, basically you have a low acid product, you can just add in the formulation some acid. So for example, you may have pickle, the vegetables, you can add some acid to it or things like that, so that the product become acidified. Once it's acidified, you can treat them like a high acid product, thereby you can have a less treatment and longer shelf life. Now, some engineers, if you are a particularly chemical engineering or other disciplines, you may not familiar with the microbiology, because I think you may not have those coursework part of your curriculum. So a brief introduction for microbiology is kind of given here. So if you look at the very small 0.1 nanometer is probably you deal with atom, whereas if you have 10 to 100 microns, you probably have viruses, flu virus and things like that. Bacteria is probably somewhere 1 to 10 micrometers, and then plant cells are much larger compared to the microorganisms. So this is kind of gives you some idea the relative size of different microorganisms. That's something we have to deal with. So what that means is, if you are going to kill the bacteria, your viruses and things like that, you are also going to destroy your plant cells and animal cells. So anytime you are going to destroy with the purpose of killing the bacteria and things like that, you are going to affect your plant cells, animal cells. That means you are going to degrade the product quality. So the challenge is, of course, how do I minimize that degradation? How do I keep my plant cells, animal cells, so that it's more intact, so that I have much more wholesome, nutritious product. So that's a challenge, as a food process engineer you deal with. Now, in terms of microorganisms, there are classifications. Psychrophiles, these are microorganisms, basically they love refrigeration conditions. They can grow well in 1 to 20 Celsius. Psychrotropic conditions, these are grow at 37 Celsius, for example, Listeria monocytogenes. Mesophiles, they can grow 20 to 40 Celsius, and then thermophiles are heat resistant, so Bacillus thermophilus. So again, we had to kind of understand some of these microorganisms, what is the best growth conditions, all those things, because when you are processing food, you need to understand, depending on where do you store, what temperature you are storing, you have to make sure these microorganisms are get rid of them part of your study. Now, you may hear the term pasteurization, and you may hear the term commercial sterilization. We will define that in a later slide, but here what we are trying to highlight is what happens when you do pasteurize or commercially sterilize, what type of organisms you are going to get rid of. You can see that when you do pasteurization, you are going to get rid of cells from the psychotropes, mesophiles, thermophiles, and maybe some of them still survive, but spores kind of survive the treatment during pasteurization. So that means you have to store the refrigerated product, pasteurized product in the refrigerators, because otherwise spores can outgrow and cause an outbreak. On the other hand, commercial sterilization, which is much more severe form of treatment, you can probably able to get rid of all the different forms of organisms. So this is something you have to pay. And then ESL is basically extended shelf life. So this is kind of a intermediate type processing. It's more severe than pasteurization, but less severe than commercial sterilization. So here in summary, pasteurization is a mild treatment, so that you can get rid of the vegetative form of bacteria. Spores survive, require refrigeration storage. The shelf life may be shorter, maybe a couple of weeks, maybe a month, whereas commercial sterilization is a severe treatment. You get rid of both severe bacterial spore as well as vegetative form of bacteria. The product can be ambient stable and have a longer shelf life, maybe 1 year to 1 to 3 years and so on. Now I am going to transition from traditional conventional technology to new processing technology. And if you look at here, and the history of food processing is going to be helpful. It's not that we humans in the modern era first invented cooking, canning, all some of these things. People have been doing this thousands of years. So before 1900s, people doing cooking, drying, salting, pickling, all kind of stuff over many thousands of years. Only in the 1900s, the industrial food manufacturing began to emerge. And in the US, this also led to Food and Drug Cosmetic Act, FTC Act kind of came in, which started regulating food industry. So 1906 is kind of give an idea. So 1900, pasteurization, commercial sterilization, these are all considered at the time new technologies. So a lot of the regulations, a lot of the experimentation on pasteurization, sterilization happened. And in the 1940s to 60s, the pasteurization, sterilization became more standards. Then they also introduced a lot of the freezing, refrigeration, those type of things became more common. And then people started experimenting microwaves and so on. And the 60s and 90s led to the development of advanced thermal processing technologies like microwave heating, radio frequency heating, ohmic heating, all those technologies kind of becoming more and more looked at. 80s to 2010, I think if you look at here, the focus kind of, if you look at the earlier years, the focus is primarily food safety and quality, but not much concern about nutrition. Then in the 80s to 2010, the nutrition become more important. So this is where the non-thermal technologies begin to emerge, where you can use like a high pressure pulse electric field. So you also not only make the food safe, but also preserve the nutrients. Fast forward 2010 to 2025, you have more and more concern start emerge about the health and wellness, also the sustainability. So that means there's a demand for clean label products. So basically people said, I don't want any more synthetic ingredients in my label statements. I want more natural ingredients in my product label, and then also want sustainable. Now this is where India may be different from Western society. We have been using plant proteins thousands of years, whereas the Western society just to begin to understand the importance of soybean and many other plant proteins. So now they call this as alternative proteins. So they start using alternative proteins to formulate some of the meat-like products and so on, so forth, from a sustainability benefits point of view. Because we will talk later on in sustainability, to grow some animals like cow or anything, it takes several thousand subliter of water. And so to create some 1 pound of meat, it takes a lot of water. On the other hand, if you use a plant protein, you can probably use much less water. So the idea here is, if you need to consume meat for growing population, it's much more difficult to do that, whereas plant protein is much more economical way of doing that. So that's basically there. And then in the future, you're probably going to some of these trends continue, and then you may also have introduction of automation, AI, artificial intelligence, many of those things get into the food processing industry. So in other words, the food processing industry never been dull. It's dynamic. It's always innovative. It's also constantly change with the consumer demand. It's that maybe one company may not change, but the rest of the companies or new players emerge to satisfy the consumer demand for innovations. Now, what are the challenges in food processing? Like by 2050, there's going to be significant growth in the world population. So, and we also see globally there's a significant increase in the middle class. It used to be a lot of affluency is in the Western countries, and the developing countries like India, China and others, probably in the 70s and 80s, they were not that affluent, whereas today the affluency is kind of spread around the globe. So that means all the people probably want more healthy food, nutritious food. So how do I feed growing population safe and nutritious food? So that's something neat. And people also said no artificial ingredients, preservatives, convenient taste, and they want to also reduce the environmental impact and sustainability. So this is from a consumer perspective. Food processor, they are there doing, it's a business for them. They are not necessarily going to freely give away samples for people. So they want technologies which can do things faster, better, cheaper, and then has a breadth of application. So in other words, they don't want a technology which probably just pasteurize milk. That's the only thing it does. They don't want that. They want maybe 10 different things that technology can help them to do. And they also want to make sure that the technology is accepted by consumers and then it's accepted by regulators. The regulators, even whether it's in India or US, you have regulations coming from international, you have federal, state, and then local. And most of them, the goal is to public safety. Say they don't care whether you are going to destroy your nutrient, they don't care your quality is bad, but they want to ensure people are not going to die by consuming your product. So public safety or food safety is the primary thing. The regulations set primarily for that. But from a food process perspective, they also want to protect the quality because you are buying from a product. If it's safe, that's good. But if the quality is not good, it's not formulated so that it tastes better and so on, the consumer is not going to go back to the same brand and buy the same brand. So you have to kind of consider that. You also have advances in science and technology happening. Like I think as I mentioned, food science and technology is a multidisciplinary. You have automation, number of engineering innovations happening. You have some of the chemistry, nutrition innovations happening, and then innovations in microbiology, all kind of integrated to make the food technology much more excitement disciplines. And then the energy water utilization, wastewater reduction is also something needs to be there. Now, when you develop a new product, oftentimes the expectation is that consumers, okay, I have a high pressure equipment which is expensive. I also have a water bottle, I can treat water bottle. So that's something not interested because consumer not going to find the value. On the other hand, when you look at guacamole or when you look at oysters and some other product, they provide unique benefits to the consumers. So the new technology, you have to be able to justify the value so that you can able to commercially sell and make sense of that. And so just doing because I have the equipment, it doesn't have a commercial value, it doesn't make sense. So you have to kind of pay attention to that. So this scale on the right is called technology ready scale. NASA, when they develop new technologies, they kind of use that. So for example, when the technology is in the lab level, this is called TRL 1. When the technology is kind of ready for industrial application, TRL level 9. So a lot of the academic research is kind of done here, TRL 1 to TRL 3, whereas some of the pilot scale research which can be done by industry as well as collaboration with academic is done TRL 4 to TRL 6. So this is something neat. Why? Because the academia can do a lot of basic research, take the information to commercial, and then have the industry to manufacture at the large scale. But you need a collaboration between academic and industry. But oftentimes, whether it's in India or US, that is always have barriers. So a lot of times the food industry want to have all the intellectual property assigned to them, so that they can able to securely produce the product, whereas the universities, they want to have that intellectual property. So, that is one of the sticking point. And then academic, for example, we work primarily focus on educating students. So, when you have a bachelor student, you have 4 years. When you have a PhD student, it may be 4 or 5 years and so on. So, it takes time, whereas the industry, for them 3 months is a long term or 6 months is a long term. So, they have a different timeline to operate. So, if you kind of talk with each other, understand the barriers, then find a way to have a common ground, build a mutual trust, then you can able to have much more synergy of collaboration between academic and industry, so that you can get more products in the market. So, this is just a highlight some of the pilot plant facilities at Ohio State. We oftentimes invite the industry visitors to come and provide short courses and things like that, so that they understand the technology. Then they oftentimes do test up their product and then get into the commercial space and so on. We provide workshops, short courses, webinars, things like that. So, you have to find a way, wide range of means to reach the industry audience, so that they can able to work with you. So, future challenge, I think food processing, as I mentioned, it is a very dynamic. So, there is going to be more challenges. So, how do we feed healthy and nutritious foods for people? How do I reduce the environmental impact? Because a lot of times when you produce food, you cannot achieve zero impact. You are always going to have some waste. How do I reduce that waste? And food packaging waste is one of the major problems facing the world today. You probably heard the term microplastics. Microplastics everywhere, that can be a major problem. So, how do I develop biodegradable packaging material, so that can survive the process treatment, keep the product safe, but once in the landfill, it can degrade faster. Right now, it is more science fiction type thing, it is not reality yet, but I think maybe people in your generation become faculty members, industrial scientists, you may be doing some of those efforts. And climate change, like I think people say climate change is not real, but at the same time we are seeing that radical climate change. You may have suddenly no rain, or you have a lot of rain. In any one of those cases, you may have a lot of losses with the crops and everything. So, food preservation becoming more important, because you kind of want to keep the processed food available, stored for longer times when you do not have a good crop yield or production. So, under those conditions, food processing even becoming more and more when you have more impact on climate change. So, in summary, food processing play a critical role in providing safe and nutritious food. It kind of virtually affect everyone in the planet one or other way, but I think we need to communicate better as a food scientists and engineers to common audience why food processing is important, because right now people just take them food processing taken for granted, but we need to kind of provide the education. And we use a lot of unit operations equipment to ensure safety and quality, and I think more and more emphasis is also going to preserve the nutrients. And food processing use a lot of energy, water, but we kind of want to reduce that. At the same time, we want to reduce the food waste, so that it can be much more economically as well as minimal impact on the environment. So, this is just to give some reading materials on sustainable food processing. So, you may take a look at it if you are kind of interested in. and so it kind of provides some idea. And with that, I think I'm going to stop here and have some time for questions. Yes.
Hello, Dr. Bala. I had a question regarding the reaction kinetics. I want to know how we can put the reaction kinetics to use when we are dealing with shelf life of food. How does that come into the picture, the mathematical model to determine shelf life of food, like when we are calculating it through accelerated shelf life studies?
Okay, sure. So, we are going to talk about reaction kinetics in the next 2 lectures. This is going to be one on food safety, the second one on the what I call the quality kinetics, and then from there we can probably talk about how do you determine processing time based on the microbial resistance for different things, or the nutrients and enzymes and so on. Then we also talk about the storage studies. So, I think basically, for example, you look at I think I am briefly telling you, but there is a extensive literature available. So, let us look at one nutrient. You want to look at how that nutrient changes over storage. And normally, if the product is kept at 25 degrees Celsius, and it may have 3 years shelf life, but 3 years doing experiments in the lab is going to be difficult. So, then you probably choose higher temperature, like for example 37 Celsius, and then see how that nutrient accelerated, deteriorated over a certain time. Then there are tables available converting that accelerated degradation to normal shelf life, thereby you can able to determine shelf life. And I think there are number of books published. So, for example, Ted Labusa, he has done a lot of publications in the 1980s, 90s about shelf life extension.
Come again, what's the name?
Labusa. I think I have one reference in the next one of the presentations.
Okay, thank you, thank you.
Hello, sir. Sir, my question is, recently in various publications, they are introducing sustainable development goal. So, in case of food science also, we are seeing the few journals, they are mostly highlight, if you can say sustainable food technology. There is a special paragraph we have to write, what is the sustainability point of view. From your, as a academic person, so what is the practical application of this sustainability? Is it how much it can be? And practical life application. Though we are claiming in each paper this is sustainable technology, that will be the novel technology, but in real scale, the ideal value what we are performing in the lab scale, that is far different from this industrial scale. So, as per your experience, can you, sir, give us any overview about the what we claim in the lab scale and how much is the industry we are getting, what is the difference percentage scenario?
Right. Yeah, I think the term sustainability is more like a buzzword. It's kind of, you have to use the term sometime to get maybe from a publication point of view or grant application point of view and so on. But I think the real understanding of sustainability and what is really needed to get the sustainable food processing is still evolving. And in fact, I think sometimes people may not even acknowledge food processing needs to be sustainable, because they think that it's probably sustainability is more from environmental or other means. Food processing is nothing to do with sustainability. But I think as I mentioned earlier, food industry is probably one of the high energy spending thing, and water. So you think about sustainability from the following way. How do I make a safe and nutritious food? At the same time, how do I reduce energy use and water use, right? And then waste reduction. So how do I accomplish that? Obviously, when you have a even novel technology, you're doing in 5 ml or 50 ml or 5 liter, it's not going to provide that sustainable thing. That metric become more valuable when you are mass producing, not only in India but maybe different parts of the world, so that it's more a real impact. Until then, some of these things are, think about this as a exercise to get you learn the principles, but may not have some real meaning at the moment. Other questions? And no questions are bad, good or bad, so feel free to ask questions. You're going to gain more by asking questions.
I also wanted to know how the industry is dealing with stress adaptability that various bacteria tend to show if they get exposed to sublethal stresses. So how does the industry deal with those kind of stresses, especially when they are dealing with disinfectants?
Right, yeah, that's a great question. Now, the stress adaptation is probably something we may not have a full grasp of it, especially with a range of different methods. Let's take a simple thing, heat. We have been heat processing various foods probably now close to 100 years. If stress adaptation is something meaningful, now we should have had superbugs which are highly resistant to heat, but we don't see that, right? Like I think for those of you not microbiologists, stress adaptation is basically, let's say you can kill the bacteria at 70 Celsius. The concept here is that with repeatedly heating the food to 70 Celsius, the bacteria become gaining more resistant, so that it requires now 75 Celsius to kill it, and then eventually 100 Celsius and so on. So they are saying when you develop processing technologies, you are killing or you are developing super resistant bugs. So that's the concept behind stress adaptation. While this concept stress adaptation is probably there, and you can see microbial population, like we have 100 people, 100 people are not same, each has certain characteristics. So the same way, when you have 100 microorganisms, different microorganisms have different resistance, so there's going to be some distribution of the resistant characteristics. But nevertheless, we have been pasteurizing food, for example milk 72 Celsius 15 seconds, even though there are agencies monitoring that. I think we haven't changed that value over last several decades. So it's kind of same. So that means that stress adaptation is important, but not necessarily something we have to too much worried about, because there are times people said we are developing high pressure processing. Now we are going to have bacteria which are highly resistant to pressure. We are never going to get rid of that, and those type of things. But these are all fear, but not necessarily practically relevant.
I would also like to extend the question and ask, how does this differ when we are dealing with biofilms? So wouldn't that be a bigger challenge?
Right. I think biofilms again, can be a challenge, but if you have proper sanitation methods developed, biofilms can be easily eradicated. So I think that way, like I think, mistake happens when you don't properly sanitize your equipment or operations. So that allow the development of foil film over time. It's just the left, what I call, on the part of the processor, they are doing poor job that led to the foil film. Then it's difficult to get rid of. But when you do regular sanitation, cleaning, all those things, we can avoid developing some of those issues.
Yeah, thank you so much.
Thank you. Other questions?
Okay, sir. Next,
Okay.
you can start the next.
Sure. Okay. You tell me whenever you want to start. You want to take? Yeah, sure. Tell me where I'll start according. It can be safe, but may not be. Okay, so now we are going to look at the thermal destruction kinetics or food safety kinetics. So when you are processing food, you always kind of interested to know how safe it is. So I mentioned milk is processed at 72 degrees Celsius for 15 seconds. How do you select that 72 Celsius? How do you select that 15 seconds? When you are processing canned food, for example, maybe you are processing canned foods at 121 Celsius for 30 minutes. Why 121 Celsius? Why 30 minutes? Why not 15 minutes or why not 45 minutes? To understand some of these questions, you need to understand the bacteriology or thermal bacteriology, because every raw product contains bacteria, and not all the bacteria is going to be harmful. There are beneficial bacteria. So we talked earlier in the morning probiotics. They are talking about bacteria present in yogurt and number of the fermented products. So those are all beneficial bacteria. We are not talking about those bacteria here. We are talking about pathogen. Those cause diseases to people, and also spoilage. Those spoil the food. And so that's kind of what we are trying to understand here. To understand that, we need to know how bacteria die when you are heat treating it. So the bacteria are basically going to look at a logarithmic order of death when they are heat processing it. What that means is you're going to have so many bacteria, then you process at say 70 Celsius for 10 minutes. You're going to reduce, let's say you have 1 million bacteria. In 1 minute, you may reduce to say 10 power 5, and then second minute, it may reduce to 10 power 4, and so on. And then you kind of keep plotting, you get something like this. So you have initially certain bacteria, and then with 10 minutes, you're going to reduce this, and so on. And then you get a plot this, you get a curve, and then you want to find out how much time it takes to reduce the population by 90%. So from say 10,000 to 1,000. So that's your called the D value. So this is kind of happens. The heating is going to basically, it's a heating time, how much time you are heating the food at constant temperature. You know, it's much easier to do in the lab environment, because in the lab you can maintain temperature everything constant, whereas when you do in the industrial scale, it's much more challenging. So that's something we'll probably talk later. So the concept D value basically is the time required to reduce the population by 1 log or 90%. So if you use mathematically, what is the time to reduce the population by certain percentage? So this is going to vary for each microorganism, and for example, there may be microorganism takes longer at a certain temperature, whereas some microorganism may be easy to inactivate and so on. So when the D value is larger, it takes longer time to process, so that means they are more resistant to heat. So when you look at different technologies, like for example heat versus radiation versus pressure treatment and so on, we will see that there is no correlation between pressure resistant to heat resistant to radiation resistance and so on. So you need to understand that. So a bacteria may be more temperature resistant, but may be easy to inactivate by pressure and so on. So you have to get understanding of all those things. So when you do this D value calculation, you are going to assume certain parameters. In engineering, we make a lot of assumptions, and then we are going to derive some mathematical relationship, and your mathematical calculations, the strength of that depends on the assumptions you make, and a lot of times some of those assumptions, when you deviate, then those calculations are only estimate but not necessarily accurate. So one of the first assumption is all the population have the same resistance. So what we are saying is, in this room maybe we have 50 people, we say all the 50 people behave the same way. We know that's not true. Each of us have unique characteristics. The same way, microorganisms, there may be millions of them, each one has its own characteristics, and so there may be some difference in microbial resistance. Second, if you have done microbiology, plating, other techniques, you probably might have counted colonies and so on. We assume that you are counting each colony in a plate. You can say that this is from one colony is one microorganism and so on. But it's possible that this one colony may have a cluster of 10 microorganisms, but you are kind of counting that as one colony. So again, we assume there is no clumping. And then there is no heat activation for spores, so that means a spore remains as a spore, and there is no injury. So injury is basically when you are heat treating it. You can say, if those of you who are not microbiologists, you can think about this way. Injury is like you get sick and you are in a nutritious medium, you kind of take a rest and then gain strength back and then start harming people again. So a lot of times when you are heat treating it, the bacteria get injured, but it doesn't die. But when you do the plate count, it may not show as a colony. You may think that it's died, but it's in reality it's still there, and with given time it's going to recover and then it's going to create harmful. So you have to use some proper medium to identify whether the bacteria is there or not there. And then we also assume that the process treatment is uniform. So when I say I'm going to process at 70 degrees Celsius in a big autoclave, you assume the entire autoclave is going to be at 70 Celsius. It's possible maybe this section here is 65, this section is 65, and then your rest of the section is 70. The bacteria in these locations can survive, then it creates a problem. So you want to make sure that if the entire section is 70, it's okay, you can have some region 75 Celsius or much higher temperature, but you don't want anything less than your 70 Celsius. So you're always going to process at the appropriate temperature or a little bit higher temperature so that you deliver your heat treatment. the thermal death time can be graphically plotted using this here, logarithmic n versus time. This is 1 over d. D is your decimal reduction time. Now, some of us are with the chemical engineering background. You may prefer this form here. You use natural log ln versus time, and then you use the k, and then you kind of use this type of equation. So, this is kind of coming from traditional chemical kinetics, whereas this comes from more traditional biology type concept, but they kind of talk about the same thing. And then these are a interrelationship between how the k and d are kind of related. So, you can also, by this extension of this concept, you can say that how many log reduction, how much time it takes to get complete inactivation. So, let us say you have a processed food. Can I say I completely inactivate microorganism in that processed food? Mathematically, you are never going to say that, because mathematically it's impossible to have complete inactivation. So, it's going to take infinite time to achieve that. So, you always pay attention. So, you can say I achieved 10 log reduction, or I achieved 7 log reduction, and so on, rather than saying complete inactivation. Thermal death time is one step forward. Basically, it takes how much time it takes to destroy the population at a given temperature. So, basically, for example, if I have 10 power 9 organisms, and then I want to reduce to 10 power minus 3, then I have 12 log reduction. Now, the question is, what is 10 power minus 3? So, is it 10 power minus 3, is it practically possible with microbiology? Generally, it is not practically do that in microbiology. It is more probability concept, which basically say that if I process 100 pouches, or if I process 1000 pouches, one of those pouches probably going to have a survivor. So, that is where that 12D concepts come in. Even though it may not be practically, you can demonstrate 12D concept in a lab environment. It is more probabilities concept. Here, it is just to give you some idea how the log reduction can be defined. So, let us say you have 10 power 5 population. If you reduce 1 log, that means you are going to have 90% reduction, then you are going to have left with 10,000, whereas if you have 5 log reduction, you are left with 1 bacteria, and so on. So, this is how the concept of 5 log reduction, 7 log reduction, all those things come into picture. Again, we can revisit this slide later on if you have questions on the d value concepts. So, in the US regulators, they define certain time, standard times for as a pasteurization time. So, 7D reduction, 5 to 7D reduction, 12D reduction, and so on. So, we said d value is the decimal reduction time for certain bacteria. So, I have here milk, meat, canned food. Is this d value is for same bacteria, or is it for different bacteria? So, the answer is the bacteria you define the d value in milk pasteurization going to be different. We will talk about that later. It is called Microbacterium tuberculosis. It is a bacteria commonly found in milk. Whereas, in meat cooking, it may be a different bacteria, E. coli, O157, or some other Listeria, and so on. Whereas, in the canning, it may be Clostridium botulinum or Clostridium sporogenes. So, in other words, the D value concept, even though this is kind of 7D, 12D, everything is same, but the bacteria associated with each food product is going to be different, because the target pathogen and spoilage organism for each product is maybe different. So, you need to make sure you understand what those resistant characteristics and then calculate your processing time accordingly. So, here I am going to just to give an example. If I have 10 power 6 viable microorganisms and you have 3 minutes at 250 degree Fahrenheit, how many minutes takes to reduce the population 1 viable cell? So, you can kind of do some of these calculations mentally and then get that, but again we will revisit these calculations later on when we do our math. What would be the final count if you have 3 million bacteria treated with 5D process and D value 5 minutes? So, you have D value is 5 minutes and you have 5D process. So, 3 into 10 power 6 and then you have 5 log reduction, that is going to reduce the population 3 into 10 power 10, and so that means you probably have about 30 bacteria left. So, a lot of these things are simple mental math, probably you can able to do yourself when you come across those things, once you get the good understanding of the D value concepts. Now, I mentioned different bacteria are going to have different D value calculations. So, for example, E. coli, you will see that it has a D 55 4 minutes. What this means is the decimal reduction time for E. coli at 55 Celsius, right. So, this is your temperature at Celsius is 4 minutes. So, if you increase the temperature to 60, this time probably going to maybe reduced, whereas if you reduce the temperature to 40 Celsius, this temperature may be different. So, you have to kind of pay attention to that. So, if you look at Clostridium botulinum D 121, that is 121 Celsius, you are going to have 0.1 minute, whereas if you look at D 121 for sporogenes 2.6 minutes. If you look at more heat resistant spore Sterthomophilus, you have about 4 to 5 minutes. So, each bacteria is going to be different. On the other side, you look at the chemical changes. For example, denaturing of proteins 5 minutes, whereas chlorophyll destruction it's going to even take longer, 14 to 350 minutes or 1 to 10 minutes and so on. One thing you will probably see here is for the same temperature, at 121, the microbes have more heat sensitive or easily inactivated compared to your nutrients. So, in other words, you probably, while some nutrients are heat sensitive, many nutrients are heat stable. So, you can able to process them even at high temperature and they survive the heat process, whereas you can able to inactivate them through heat treatment. So, that is something we have to compare. So, you always try to compare the food safety side and then the nutrition side to get some assessment. The D value is influenced by the composition. So, for example, there is an organism called P83679, which is the Clostridium sporogenes. If you do in a cream style corn, it has a D value about 2.47 minutes, whereas if you do in phosphate puffer, it is 1.31. So, a lot of times in the academic environment, we may be doing microplates using the buffer solutions, and then we expect that holds good in the real food systems. It may not happen. So, you need to make sure that you understand what the survival in the actual food product itself. the microorganisms also, the D value of the microorganism influenced by the type and strain, the composition, your pH and water activity. So, we saw earlier pH is an important factor which affects the survivability of microorganism. So, if a microorganism neutral pH and has a D value of 1 minute at 60 Celsius, if you acidify, then the D value may be go down. Instead of 1 minute at the same temperature, it may become 0.7 minutes or 0.6 minutes because it is an acid environment, or it may be completely inhibited. So, you have to consider that. And then you also have to consider the agent stage of the cell growth, but normally when you are doing processing in an industrial environment, you may encounter what they call wild bacteria. So, that means these bacteria never come to the lab, it just stays in the nature, and they may have highly virulent characteristics. So, you know, when you are an industry person, you always try to monitor those things and then make sure that your process is properly developed for that, and then at what temperature you are kind of processing. And this is a mathematical relationship which kind of help you to estimate the D value at any given temperature. So, the D0 is the target D value at your particular temperature T0, whereas this is your reference temperature here Tt, and the Z value is your thermal sensitivity of the bacteria, which we will talk in the next slide or in the coming slides. When you look at the D value, the increase in temperatures, you can kill more bacteria. So, you can able to change the D value accordingly. So, if you have a D value of 1 minute at 60 Celsius, you increase the temperature to 70 or increase the temperature to 80 or 90, the D value is going to go down. Instead of 1 minute, it may be 0.5 minutes or 0.1 minutes and so on. So, you are going to have certain benefits. So, normally it is a known fact in the industry, high temperature short time is better because higher the temperature, you inactivate the bacteria quickly with the less time. At the same time, lot of the nutrients are heat stable. So, higher the temperature, it may not affect the nutrients that much. So, you may have still a nutritious product, but less in terms of microorganisms. The next concept is the Z value. Because different bacteria have different sensitivity heat, some are more sensitive, some are less sensitive, we use the term Z value. Basically, it is the temperature range in which you are going to have a 10% or 10-fold change in D value. So, if you plot your logarithmic D value versus the temperature, you are going to have certain change in the D value, that is your Z. So, normally it is kind of given for certain microorganisms. So, for example, Clostridium sporogenes, it is a Z value of 10 or 18 degree Fahrenheit. So, usually people kind of assume, particularly when you do canning, those kind of data is kind of calculated. Now, some of these concepts, D value, Z value, remember these are not modern concepts. These concepts were developed probably in the 1920s and 30s, and then still we are kind of using, adapting over time. So, that means these are all tend to be a little bit more empirical. So, there are certain terminologies people use and so on. So, we kind of adapt some of those terminologies with time. And then with the chemical kinetics, we kind of try to take that biological concepts and then try to convert it into chemical concepts and so on. But still, people use both sides of the equation. So, when you are talking about chemical reactions, you are going to use the term activation energy EA, and then the temperature T, and then your rate constant K and K0. Basically, it's the same similar equation we saw earlier for D value, which is relating your rate constant K with a certain temperature, certain constant value K0, and then activation energy, and then the temperature. The R is the universal gas constant. So, again the units basically consistent with the how the K values are defined and so on and so forth. So, again trying to relate the biological concept logarithmic D versus logarithmic natural log ln, you are going to get two separate relationship, and then from there you can relate activation energy and EA value using this concept equation here. So, the point here is it is possible to convert the chemical kinetics into the microbial kinetics, vice versa, but I think these are in today's environment, a lot of these databases are readily available. You do not need to memorize many of the details, you need to know where to look for those information and then use it. So, again here the Z value for bacteria, you can see the Clostridium botulinum, I said 10, but it is in the range of 8 to 12, Sporogenes 9 to 13. On the other hand, if you look at the destruction of diamine 20 to 30, whereas denature of protein 5 to 10, enzyme inactivation 8. So, what this tells me is if I have certain log reduction of Clostridium botulinum, let us say like 8 to 12 means 10, you may have more enzyme inactivator under those conditions, because the Z value is going to be 8. So, if you increase the temperature, you are going to have more enzyme inactivator as a result, because they are more sensitive, whereas the botulinum is a little bit more stable. On the other hand, your time in destruction is 30. So, they are kind of relatively very heat stable. So, you are not going to make major changes in the time and value when you change the temperature from one to other. So, when you kind of try to evaluate your process design, you have to look at the key nutrients and the target microorganisms, and then try to kind of play around, how many log reductions of bacteria I need. I basically need certain log reduction, because nobody want to eat bacteria containing food, but people are also willing to eat maybe less nutrition, but they do not want to have unsafe products. So, you kind of play a trade off. The next concept is the F value. So, the D value kind of says, okay, in my thing I have bacteria and I am treating certain temperature, and under those temperature what is the time it takes to reduce the population by 90%. The Z value kind of tells how different bacteria are sensitive to different temperatures. So, let us say that I have a raw product, let us say like I have a raw meat and I have 10 power 4 bacteria, and then let us say that I want to, so the A, let us say the initial population is 10 power 4, and then I want a final population 1, which is also equal to 10 power 0. So, the F value basically going to calculate what is the decimal reduction time for the bacteria, what is the logarithmic A and logarithmic B value. So, in this example, if I have a decimal reduction time of 1 minute, so then the F value is going to be 1 minute times 1 times log 10 power 4 minus log 10 power 0. So, that means 1 into 4 minus 1. So, you are going to have certain log reductions there. So, that is kind of how you kind of trying to calculate. So you probably, so the units here is, this is in 1 minute. So this is in minute. So that means this value, F value, is going to be in minute. So in other words, I have a certain population, I am going to reduce the population from one value to another value, how much time I am going to process it. So in this case, I may be processing about 3 minutes. So that's your F value calculation. So in this calculation, I did not consider the temperature variation, right. I kind of assume that the whole thing happens, let us say this is at 70 Celsius. That means I assume my vessel is at 70 Celsius. But in reality, your process equipment, you are going to start with room temperature, and then it is going to take certain time to reach your processing temperature, and then you are going to cool it down. So, all those time, come up time, and then cooling down time, all those things we are not considering. We are just trying to keep it simple, and this is where the F value concept is kind of sterilizing value concept coming in. So, this is the equivalent minutes at a reference temperature. So, here just a worked examples. You can say, okay, at 250 degrees Celsius, like you can say the Z value for microorganism is 18 Fahrenheit. This is normally used Clostridium botulinum, 18 Fahrenheit or 10 degrees Celsius. And then basically it is going to say how many log reduction you need. If you have 250 is 1.16, you need 6 log reduction, then you approximately need about 6.96 or about 7 minutes. So, you can able to do some simple mental maths. But here, as I mentioned, it does not consider the temperature distribution. It is going to, in reality, it is going to take some time to reach the temperature, and then you are going to have a heating period and you are going to have a cooling period. It does not consider. It always assumes I am going to be at the temperature, say 70 Celsius all the time, but it does not come look the temperature to reach the 50 or 70 Celsius and then temperature to cool down, it does not consider. So, then we are going to go next one, we will come to that in a minute, but in the literature the F value calculations for different products are given. So, for example, asparagus about 4 minutes, corn 6 minutes, loaf and so on. So, somebody has done these experiments. So, maybe we will wait for the current to come back and turn the projector on before we can get into additional class. Is it recording still or? Recording is going on. Okay. Okay, good. So, we continue the lecture. So, as I was telling you earlier here, somebody has done the experiments. So, when they say F0, it may be 250 Fahrenheit, and they kind of put some of these different products, and then I estimated how much time it takes to get certain log reduction in different products and so on and so forth. So, there are databases available in the US, what they call National Candidates Association. They have published books that has lot of these data available for different food products and so on. So, in other words, if you are a new person doing canning today, you do not have to start from ground zero. You can always look at some of those reference sources, and then you can look at your formulation, and then you can be able to develop your calculations accordingly. So, the next equation we are going to use is this relationship here. Log Ft is going to be this here. So basically, when I have a canning equipment, initially maybe at 25 degrees Celsius, and then it's going to go to 121 Celsius, and then you are going to process say 30 minutes, and this come up time maybe, I'm just making some numbers, 15 minutes. Then you are going to cool it down maybe another 10 minutes. So how do I compare some of those values? So you can probably use this relationship here. So this F0 is basically your reference temperature. So if you are doing at 121 Celsius, then this is your lethality at that 121 Celsius. And this Z value is the Z value for your target bacteria. And then this is your temperature, and this is your reference temperature. So I have one worked example I can show you in the spreadsheet the next once we finish this lecture, so you have a better picture of that. So essentially what we are trying to do here is, when I start here, I'm going to take this temperature history data, and then I'm going to divide this into smaller time segments. And then I'm going to look at, for each segment, how much accumulation of bacterial death happens. So in other words, when I start at 25 degrees Celsius, the temperature is very low, the bacteria may not have any death happening there, whereas when I probably approaching close to 100 Celsius, it's going to have some lethal effect. So there's going to be some death happening. So I can consider that death. And then when I reach my target temperature, for sure the bacteria is going to die, and I can calculate that. And then when it's going through the cooling section, there's going to be some death happening as well. So in other words, the death of the bacteria when you are heating, cooling in an industrial environment can happen during the preheating side, during the cooling side, as well as cooling. And then you have to able to mathematically calculate using this relationship what is the total death happening at different stages. However, you don't want to take credit for bacterial death in all those time intervals, because you kind of want to do things much more conservatively, and you can probably able to calculate things accordingly. Normally for Clostridium progenies and Clostridium botulinum, at 250 is the reference temperature, and your Z value is about 10 degrees Celsius. For vegetative bacteria like E. coli, Listeria, you use a reference temperature of 80 or 60 Celsius, because pasteurization is somewhere around 70 Celsius, and depending on the resistance you may use 80, 60, and then your Z value is between 6 to 9. So these are all empirical values based on the industrial experience. So this is kind of the temperature distribution curves I kind of talked about. The red one shows the temperature inside a canning retort, whereas the blue line shows a convection treated product. So if you have a juice, it can reach the temperature of the retort quickly, whereas if you are processing some meatloaf or something, the conduction heating takes place. So the come up time is going to be slow. You're going to have this longer come up time, and then you're going to have this cooling down. So you have to accommodate these temperature curves in your mathematical calculations to get your total processing time. So for that, basically you are going to take that curve and then divide them into small segments, and then you are going to assume what is the microbial lethality happening in that particular section and what time. So let's say this is 1 minute interval, then I'm going to calculate this as a 1 minute interval. If it is 1 second interval or 5 seconds interval, then your time is going to be different based on that time interval concepts. Then what I do is I kind of calculate the values in each segment and then kind of sum them up so that you can get the accumulated lethality. It's a good idea to learn how to do this in by hand or with the computer by yourself as a student. Later on, when you go in the industry, you're going to have software available where you input certain parameters. The software is going to provide all those calculations for you, but it's always good practice to know the math so that you can verify whether the computer is making any calculation errors and so on. The next one is the spoilage probability. The spoilage probability basically going to tell what is the likely that a product going to spoil. So, let us suppose you are going to have a bacteria where it's going to have total number is about your processing R. So, R is the total number of containers, and if you have a N1 as the initial population, N2 is the final population. So, based on this your F value calculation, you have certain decimal reduction time. So, initial population is R. So, each container has N1 population. So, you are processing R cans. So, R times N1, and then the final population is you are processing again R cans, and then population is N2, you have N2. If your probability of reducing that spoilage is to 1, then this become 1. Then from there rearrange the math, you can calculate R is 10 power F over D divided by N1. So, this can kind of help you to determine what is the likelihood you can have spoilage happening in a particular canned product and so on. So, you have in this example you have a 2 into 10 power 5 organism per container and you are processing for 45 minutes. Your D value at 118 is 3.5 minutes. So, here whenever it says you are processing for certain time at a specific temperature, that leads to your F value, because F value kind of tells you how much time you are processing it, and then D value is your decimal reduction time, and then your initial population is 2 into 10 power 5. So, it kind of provides that. So, 3 into 10 power 7. So, what does that means is if you process 3.6 into 10 power 7 containers, one of them likely to spoil under those conditions. Now, as a processor, is this my acceptable risk? So, you can probably say, okay, I can use a milder processing, I can accept 1 container out of every 10,000 containers spoil, then you can maybe reduce your spoilage intensity of treatment, or you can increase the intensity of the treatment so that I can have 10 power 7 containers out of which 1 container spoil, or I think I am making billions of cans every day in my factory, I do not want this much spoilage, then you can increase this number to maybe 3 into 10 power 9 or some other value which is acceptable. So, each company, depending on whether it is a smaller or larger medium sized company and so on, the spoilage probability can be adjusted. Again, here you are going to have some mental math things. You can able to try to look at the processing time. So, again, one thing you have to look at some of these things is when you look at these type of problems, before you try to get into math and solve the math equations to get the answer, think physically. So in this example, I am processing a 121, 8 minutes, Z value is 10. What is the equivalent minutes at 115? So I am processing 115. Would you expect the processing time more or less? It's going to be less, right? Because you are going to process, it's going to be more because you have 8 minutes, 8 minutes. So 115, your processing temperature is reduced, so it takes longer to kill the microorganisms. Same way here. So you probably go back to this equation here. Ft is F0 10 power 1 minus Z T minus T reference. You kind of use this type of equation and then you substitute the values and then you can do the calculations. F0 for a canning retort is 6 minutes. What is the equivalent minutes at temperature 126? So normally when canning, they assume F0 is at 121 Celsius. So it's 60 minutes, 6 minutes. So when you increase the temperature 126, so the processing time going to be shorter because you're going to treat with a higher temperature. And then you can do the math. And then similarly, you have third example problems and so on. So here are some solutions. So 115, you have F value is 8 minutes and your processing time 115 minus 121, Z value of 10. So it's going to take a longer time to achieve the equivalent kill than a lower processing temperature. So here's the solution for the next one at 6 minutes and then 126 minus 121 divided by 10. So you can have short time to achieve equivalent processing time. And again, this is just going to show you takes 10 minutes at 240, 250 it's going to be much shorter, 2.7 minutes. At 260, 10 minutes means 250, it's going to be much longer time and so on. So there are variety of these things you can probably try to solve yourself. You can use a calculator or you can use a spreadsheet for doing some of these calculations. So these are some selector reading materials. This particularly talks about the kinetics. In this lecture, I primarily covered the basics for thermal processing or heat treatment. The same concept can be applied to radiation, microwave, or Omi heating, pulse electric, high pressure processing, all those things. So this has an extensive review published in 2002. FDA kind of had a contract with number of people and they had a big review done. So this is kind of documented. So if you are looking at the new processing technology, this is a very useful information. And then you probably have some traditional kinetics relationship. So this may be on the book chapter or book material you may find useful. So with that, I think I will stop here and then we can probably have some questions and discussions. And remember, the reaction kinetics and chemical kinetics, these are the foundation for food processing, especially designing the safe food processing, whether you use thermal processing, non-thermal processing. The concepts we learned today, these are all extended by different things. So it's always good to make sure you understand these concepts.
Anyone having any question? Sir, I have only one doubt.
Mm-hmm.
So during my MTech, so I go to visit to the industry. So they are mainly export the dehydrated item. You can see that's onion, garlic, or potato cubes. They reduce the moisture content about 6 to 7%. Then they irradiate. Also, then they go for the ozone treatment, and then they export to the US country. Sometime there is a microbiological issue, because of that the container will be totally rejected. After applying so many things, still there is a chance of microbiology. So which technique that you think they can avoid these problems? Because in entire year they can save more than 200 or 250 containers. Among them, 20 to 30 containers already rejected. Every year, we still trying best technology. During my internship, still now we are facing the same chase.
Okay, sure. So is this a product? What's the product and what is the
onion powder?
Onion powder. So this is raw material is onion powder.
Yes.
And then it's treated by some dehydration.
Then they grind it in a fine powder. Then they sieve it. As per the sieve size, they simply market it. After for adding calcium citrate to prevent the moisture migration, double layer polyethylene pouch, then irradiation as well as ozone treatment. Still now it is like.
Right. I think it's quite understandable they have the challenges because you are dealing with what they call low moisture content foods, and
Yes.
basically these onion powders, they have water activity is very low. When you have a low water activity, then doesn't matter how intensive a treatment, microbes likely to survive in your product. So I think one of the simpler solution maybe try to have better control over the raw material quality. So in other words, I think have the supplier try to provide better quality raw ingredients so that you have less microbial load start with, then you're going to have better chance of reducing some of the microbial load. Because normally many of the processing technologies we talked today, these are all valid for high moisture content food. When the water activity becomes low and low, these techniques become less and less efficient, even thermal processing, irradiation, and so on. So that means you have to use extremely longer processing time, and when you do that, it may affect quality adversely. So it's kind of the trade-off. So one of the better solutions is try to look at the ingredient suppliers. Can they able to have a better control over the raw ingredients so that maybe they can able to reduce that microbial load, then you have less issues.
Okay, sir. Thank you.
I have a very basic question. How do we know how many log reductions we want? For that, do we have to know the initial load, microbial load? Like for example, if there is almond processing and there is some heat treatment that the almonds are going through, how do we know how many log reductions we want in that?
Right, sure. Yeah, that's a very good question, right? So I think the log reduction during different processing methods, whether pasteurization, sterilization, or low moisture content food type of things and so on, it all defined by the regulators. So in this case, I think I'm primarily talking about the US FDA or USDA type of thing. So they define 5 log reduction, 7 log reduction, and so on. Your question also bring in other interesting thing is how many log reduction is sufficient, right? So I may have a raw material which start with the initial population of 2, and then if I had a 7 log reduction, you may have 10 power minus 5 survivors. I may have a raw ingredients with the 10 power 4 population. If I had a 7 log reduction, then the populations are above is 10 power minus 3. So essentially what we are trying to do is, by controlling the initial microbial population, I'm kind of increasing my opportunity for reducing the food safety risk. So it's more of probabilistic concepts, right? So do I kind of, a lot of the major processes, rather than trying to get all the product and then try to process severely and then achieve reduction, they have quality control programs for the farmers or suppliers. So they tell, okay, I'm going to reject the raw material if the raw material's initial microbial population is less than or above 10 power 3 or 10 power 2. So they're going to have that, and then they are going to reward the farmers based on those numbers factors. So thereby they have a high quality raw ingredient, in the sense it has a less microorganisms, so that they can also have better opportunity for retaining the product for a longer time, reducing the microbial risk, all those things. That's probably one way. Whereas if you have a raw product with a lot of problems, initially, then they may probably going to have potentially rejections, all those things.
Sure, because when they are using surrogate bacteria on, say, for example, like I mentioned, almonds, there is a set limit of those many log reductions that need to be achieved. So I was really curious to know from where they get that, how do they decide that that has to be the number of log reductions when they are using a surrogate?
Right. So again, you're introducing another good term, the surrogate organism versus the what they call target bacteria. So those of you who are not familiar with the term surrogate, so normally when you do food processing, you are going to use the bacteria like Clostridium botulinum or E. coli. These are all the pathogens. But in most of the industrial environment, they don't allow the bacteria, pathogens into the processing plant. So you have to use a non-pathogenic bacteria which has a similar characteristics as your target pathogen, and then you do those studies with that surrogate organisms. Then they are going to look at the resistant characteristics, and then what they do is they are going to look at historical outbreaks, right? So, in meat, how many log reduction, what's the common growth of spoilage organisms or pathogens, or in almonds, what are the things, and then they may decide, okay, approximately 5 log reduction is going to make the food safe, whereas in some products you may have to have a 7 log reduction to make the food safe, and so on. So for example, in the case of apple cider, when you are picking apple from the tree and then you are making cider, the FDA sometimes allow, you can also reduce the population by removing the microbes from the apple. You may get 1 or 2 log reduction, and then you may be using a UV treatment or heat treatment. You may get a 2 or 3 log reduction there, and then you can able to take advantage of combining this and that to get a greater log reduction.
Sure. So then they will have to monitor the initial log.
Normally, they don't do the initial log reduction. Okay. Because if you try to do that in the industrial environment, it becomes a nightmare. Because today you may get a batch with a 10 power 3 population. Tomorrow you may get a batch 10 power 7 or 10 power 4 population. So the way to avoid that variation is you kind of make your supplier accountable. Okay, you are going to consistently give me 10 power 3 population. I'm going to do a quality inspection. I'm going to reject the batch if you're going to exceed that limit.
Sure.
So then you're going to have that built-in safety mechanism, 7 logs. So that's your acceptable risk, how much risk you are willing to take. In the case of canning, you go to 10 power 10 or 10 power 12, it's higher risk, whereas in the case of pasteurization, it's relatively lower risk.
Thank you so much.
Mm-hmm.
Thank you.
Anyone having any further questions? Okay, so we'll take 15-minute tree break, then we'll continue.
Sure. Sure. Sure.
Okay, welcome back.
So here we are going to talk about the reaction kinetics in food quality. So in the earlier lecture we talked about the food safety and looking at the reaction kinetics. Now we are going to talk about the kinetic approach for estimating food quality. So if you look at food, it's a highly complex biopolymer. In addition to microorganisms, food probably contains a lot of different materials, like you may have vitamins, you may have proteins, lipids, carbohydrates, and when you are heat processing it, pressure processing it, it's going to produce a lot of changes. So the quality of the product you are processing depends on how much time you exposed with heat, pressure, number of things, and what changes you are causing them. And in addition to that, a lot of the fruits and vegetables, they also have enzymes. These enzymes also probably cause deteriorative reactions in addition to the spoilage microorganisms. So you want to kind of control them. So for that you need to look at the enzyme inactivation. When you are heat processing certain substances, like for example sugars or lipids, proteins and so on, you may have certain crystallization, aggregation of substances may take place, and as a result you kind of trying to have understanding of how these different components going to affect your product quality. So if you look at the reaction kinetics, we talked about microbial reaction. The biochemical reactions also have a similar concept, except it may be using more chemical reaction kinetic equations we used earlier. And some of these reactions may be reversible or reversible. In other words, you may have enzyme completely inactivated, or the enzyme may inactivate and then maybe recover if there is a need. And it also depends on the treatment intensity and the storage conditions. So for example, if you are storing at 5 degrees Celsius, the quality of the product probably going to be remains much better, because at low temperature some of the deteriorative reactions going to be less, so you can able to store for a longer time. Whereas if you are going to increase that to room temperature and you don't have appropriate packaging material, you may deteriorate much more quickly. So during the break I had a conversation about accelerated storage studies, where somehow some of these deteriorative reactions can happen, and how you can able to minimize those, and how do you predict some of those things with the shelf life testing. So, the goal here is we kind of develop process condition where we want to have some of these reactions can be desired. So, you can able to increase them, whereas some reactions are undesirable, you want to kind of reduce them to the extent possible. You may not be able to completely reduce the reactions, but you can try to minimize them to the extent possible. So, if you look at different substances, like for example, protein, it may go through various reactions, like it may denature, it go through hydrolysis, it may have certain Maillard reactions and so on, and that may result in precipitation, solubility, and you may have some anti-nutritional factors, for example, in some of the plant proteins and so on. Whereas, if you have certain vitamins, you may have oxidation, and then you are going to lose the nutrition value and so on. So, you kind of look at different products, different components, and then try to understand how some of these chemical reaction kinetics can help you to have much more stable product. So, chemical reaction kinetics use a different set of mathematical equations, and so essentially, suppose I have a particular product with a certain concentration, and I am going to process for a certain time, and I am going to generate a curve, and then in this curve I am going to calculate the slope, and then that slope is going to give my reaction rate constant. So, this particular value, maybe I have certain ascorbic acid in maybe in a juice, how much ascorbic acid initially I have, and then as I am heat treating that, how that ascorbic acid kind of reduce. And initially it may have certain concentration, and then with time how that change over particular time at a particular temperature. A general form of equation is the change in concentration with time is a constant K, C, that is a concentration, and then a term N, and then depending on different reaction rates, like you have 0 order reaction, first order reaction, second order reaction, different reactions can come in the system. So, 0 order reaction basically assumes that the rate of reaction is independent of concentration of the material. So, in other words, I have certain concentration of my ascorbic acid, and then that change in ascorbic acid value with time is independent of concentration. So, if I had 100% concentration, or I had 75% concentration, or 50%, it is immaterial. It is going to decrease maybe 5% every minute I am processing. So, then you can able to say dC over dt is just a constant 0, and then by solving this equation you have this relationship C minus C0, that is your initial concentration, and then you are going to reduce over time certain value and then get this. And so, you can able to get this type of 0 order reaction. So, when you have, for example, non-enzymatic browning of whey powders, things like that, you can see that this is kind of follow 0 order reaction, and then for each temperature you are going to have certain K value. So, you can able to get that value. The second one, the value is going to change as a function of concentration. So, in other words, if I start with 100% orange juice, or I start with 50% on orange juice, the degradation rate may be different depending on my starting point. So, you may have more degradation in one case and less degradation in second case. So, this is where you are relating the degradation with the time as a function of both the rate constant and the concentration here. So, this is your first order reaction. So, here some of the typical problems this may use this type of first order reactions are when you look at degradation of color pigments, enzyme inactivation, things like that, you are going to have first order reaction. So, in other words, the rate of degradation of enzymes is not only dependent on the time, but it also depends on how much quantity of enzymes initially I had and so on. So, it can kind of lead with that type of thing. And then the same with the truth with the color pigments. Then you can keep going second order, third order, nth order and so on. But normally in food process operations, you are going to have 0 or first order reactions, and then you can kind of do that. Now, if you are a beginning user, one of the questions people always ask is, you have a raw data, and then how do I decide it's a 0 order or first order? So, one way to probably look at is, you can do a set of experiments and then you can plot them but both 0 order and first order, and then see whether it makes sense. So, if you look at this data here, the data sets here, you can see the data present even here, whereas if you use a 0 order, you are estimate you are saying everything is kind of completely depleted in 200 days, whereas in reality even in 300 days you have something there. So, this is much better fit with the first order reaction and so on. So, by simply mathematically playing with these type of orders, you can see which one your particular reaction may be much more suited and so on. So, this is regarding the second order reaction, and again you can have a solution, and then you are going to have a hyperbolic relationship between the concentration of the reactant and time. So, previously the concentration is just first order, now here it is a second order. So, you are going to have a parabolic relationship, but this type of reaction is not that common in food processing. So, probably for most of the operations you do not need to worry about it, but one example is lysine loss in milk, maybe kind of give an example for second order reaction. And for the sake of completeness, you can think about nth order reaction, which can be related like here, so that you can probably get this type of things. But more commonly 0 and first order are much more common in food process operations. The next concept we talked earlier is the activation energy. So, activation energy is the minimum energy required to start a chemical reaction. So, when you are kind of heat treat or when you are doing different processes, to initiate a reaction you need to provide or supply certain energy, and so what is that minimum energy is the activation energy. So, the relationship here, the reaction constant K is related to activation energy EA and R, which is the universal gas constant, temperature T, and then you have a constant A0. And then you can kind of simplify this with the logarithmic graph, and then you can able to get the slope EA over R. That kind of gives you how different reactions going to affected by this activation energy. So, this here the activation energy values for different reactions are given. So, if you look at here, protein denaturation 350 to 500, and if you look at spore destruction 250 to 335, whereas if you look at enzyme reactions 0 to 34 and so on. So, in other words, if you look at some of these things, some of these reactions probably going to go much more quicker, whereas the spore destruction going to take much more energy, whereas the other things like protein denaturation require even larger amount of energy. So, the Q10 is basically a empirical relationship that can relate what happens to a chemical reaction when I change that to from one temperature to higher temperature. So, let us assume that I am processing at 70 Celsius, and then I increase the temperature to 10 degrees. So, that means from 70 to 80 Celsius. What type of changes probably happening? This may be related to the enzymes, flavor, degradation, enzymatic browning and so on. Then you can say that based on those changes, for every 10 degree change, it may increase the shelf life by certain factor if I have a Q value of 2. So, in other words, you calculate the reactions Q10. So, at reaction temperature 1, reaction temperature 2, and if this value is 2, then in this case if I change that value by 10 degrees, my reaction is going to increase, our shelf life is going to increase the factor of 2. Now, what is shelf life is defined, right? Again, shelf life defined meaning may be different to different people. Some cases it is simply a microbial reduction. So, I have certain microbial reduction. If I increase that microbial reduction, or I get the microbial contaminants, then my shelf life is over. In some cases, I have certain nutrient. So, I may have certain ascorbic acid, and if the ascorbic acid falls below a certain value, my shelf life I can define that's over. In a different sense, I may say, okay, if the shelf life is limited when the consumer acceptance is below, that becomes much more subjective. That may not follow these type of things. When some of these select choices are based on chemical deterioration, based on nutrition or texture change, color change, all those things, or based on the microbial, then you can able to use this for doing shelf life testing or estimating the shelf life and so on. Whereas, if it depends on sensory, then whole set of parameters come in, right. If your audience is young population, or if your audience is mature adults or senior citizen, the expectations, desired characteristics, all those things can be different. So, you may have to use a different set of criteria for those type of conditions. So, mathematically the shelf life can be Q10 can be calculated using this relationship here. You have activation energy EA over R, universal gas constant, and then you have two different temperatures where you have done these type of things. And in the past, I think for example, US Army for their meal ready to eat MREs publish a lot of shelf life studies, because when you have a product with a shelf life of say 1 year or 180 days, you have a longer time, and you don't want to sit and do those experiments for 2 years to see what happens. So, what they try to do is they arbitrarily pick certain higher temperatures. So, for example, instead of 25 degrees Celsius, they choose a temperature 37 Celsius. Then you are going to have set of kinetic parameters for microbial destruction or enzyme or quality destruction. Then they led that back to the changes happening at 25 degrees Celsius. So that way they can able to say, okay, if you're going to have 37 degrees Celsius, my shelf life is so many days, then that's equivalent to a shelf life of this in 25 degrees Celsius and so on. So this topic was very popular in the 1970s and 80s. There's a professor by name Ded Labusa. So he has published a lot of different papers on shelf life testing. So if you are interested, you can probably take a look at some of the papers. I think I have one reference cited in the reference list as well. So here's just a given example problems here. So I have a sucrose, it's being inverted at 80 degrees Celsius. It's probably about 50%, and the time is about 9.1 minutes, and then 90% after 30.3 minutes, 99% after 90 minutes, and then you calculate the reaction rate constant. So in many of these problems, you kind of take that problem, read them, understand the concepts, and then put them into some type of table so that you can able to make a graph and then do your calculations. So you have processing time or the time, and then your concentration, and then you're doing the logarithmic concentrations, and then you're going to plot them with the time, and then you're getting your slope, and then that's going to give you your k value constant. And again, some of these things you can probably go back and try to do by yourself, so that if you are not done already. And again, those of you have taken engineering classes, you probably have gone through this type of exercise before, so it's nothing new for you under these conditions. So why do we do this type of calculations? So in this previous example, so basically what we are talking here, this type of experiments, what if I want to know what the concentration at 15 minutes? Because here initially we were doing at 9, 30 and 90 minutes. Now I want to find at 15 minutes, which is between these two values. So once you have an intermediate value, you have the equation, you don't need to do the experimentation. All you have to do is you kind of identify your processing time, 15 minutes, and then you substitute the values, and then you already have the k values calculated earlier. Then you can able to calculate 0.32. So in other words, these type of kinetic equation help you to find out what if type of scenario. So what if my values changes when my concentration is increased, or what if I'm going to treat this many minutes and what happens and so on. One case in this example you don't want to use. So for example, I have a processing time here, say 0.9 to say 90 minutes. But if I want to find out what is this value, for example, at 100 minutes or 120 minutes, this is not good, because you are going to extrapolate that calculation. Because when you do these calculations, you are going to estimate your slope based on certain curve fitting in a certain region. And then when you are extrapolating here, this data may go linear, or it may go like this, or you may go like this. We do not know. So extrapolation of this data is always discouraged. So you don't want to extrapolate that information, but within the data set you can interpolate and then able to make the estimation. But this is a common mistake number of people make, so make sure that you don't do that. So here basically, like a, let's see, you have another problem. You have different temperatures, sucrose concentration, and K values are given. You want to calculate activation energy and then reaction rate at 383 Kelvin. So all these example problems try to make you to go through use the equation, get the values so that you get a practice of solving them. So you have the temperatures given, K values given. So you're going to plot the values in the graph, and then you're going to calculate the activation energy as a slope, and then you will estimate that value. Once you have the activation energy, you can able to formulate an equation, and then you can able to estimate the value at particular temperature. So here you have this slope, and then here you have the EA value, because you're going to assume that the R value is a constant. Normally you can able to obtain from reference books, or it may be, if it's in the exam, it may be given. So you can able to calculate your K value, and then once you have this value at 383 Kelvin, you can able to calculate this as the value. So one thing I noticed here, if you look at the data here is between 273 to 323, whereas I'm asking here to calculate 383. So I'm kind of violating my thing, but not all the time. This is a math equation. When you put the numbers, the math is going to give you some numbers. It may work fine because the relationship linear, and you extend this, it still may linear, but you also have a chance it may go through a nonlinear part. So it's always good practice, do not extend that relationship, because when you do calculations with the calculators, they always give out some numbers, and if you don't relate the number to physical reactions, you may just very confidently say my reactions are right, but it may not validate what's happening in real life. So you always check, is it reality happening there or not. So again, this is just an example problem. Again, you have kinetics of polyphenol oxidase in mushrooms is assuming first order reaction. You have rate constants given 0.09213. Calculate the activation energy for inactivation of polyphenol oxidase. Again, you can probably look at these values and then use this relationship to calculate the slope, and then once you calculate the slope, that value is EA over R, and from there you can estimate your EA value, activation energy value. So these are just some references. So this is one of the classical thing on chemical kinetic deterioration in foods, and I think it's published in Journal of Chemical Education. I think there's a free PDF you can download from the internet, so you can probably take a look at that. This is also another good paper on kinetic modeling, and it's also published in Comprehensive Reviews in Food Science and Safety. So these two probably may be a good source for you to learn more about this topic. With that, I think we can probably stop here, and then we can have some discussions. Again, the topic of chemical kinetics is so broad, but I'm kind of trying to cover them in a shorter time. But I think once you understand the basis, you can probably get into other details more later.
Okay. Anyone having any questions? Sir, I have only one doubts.
Mhm.
So basically, when we design any equations, so we mostly prefer the zero order modeling, first order and second order linear equation. But mostly in ideal situation, we are preferably go for zero order or linear equation. But in practical scenario, it may be non-linear equation. Can you suggest any software or any kind of things where we can generate new equation like non-linear equation instead of linear equation, which can be found in everywhere?
Right. You know, like again, some of these things, it all depends on how much data you have to process. You know, Excel itself can probably provide some of these curve fitting and slopes and so on. And then you can also probably use what if scenario, like for example, you ask the software to fit this with a zero order, first order, and then try to make a plot with the zero order, what type of predictions it has over time, whereas first order, what type of prediction, and then you can able to get that. So one of the challenges, of course, is how much data you collected and then how much duration is there. So for example, if you have to do an experiment for 365 days and then you only had 180 days data, and you may fit that as a zero order reaction. But when you conduct the whole set of experiments 360 days, it may become a first order reactions. So you may be underestimating certain values under those conditions. So you have to kind of look at the comprehensive picture. And from an industry point of view, a lot of times they prefer simpler is better. So you don't want to have second, third, or fourth order. It may look fancy from a math point of view, but they want everything simplicity, because what they want is in real life is that match the reality of physically what's happening in the food.
Most of the time I found either zero order or first order is the best fit model.
Right, right.
So mostly when we are applying some new model, we are trying to develop a new model. So for that we mostly using Origin or some kind of MATLAB also there.
Right.
But still there is a problem to develop in a new equation.
Right. You know, I think the simpler answer is, from an industry perspective, keep it simple. Zero or first order is much more easy to understand and describe. So you can able to do that. Whereas once you get into nonlinear, third, fourth order and so on, it's mathematically difficult. So I think try to avoid to the extent. It may be interest from an academic point of view, but it may not be much value in a real life situation.
Hello, sir. So as you told about the example of army, sir, the army that they are looking for the greater self life. So why industries are not preferring for the greater self life in the for the common people? Did they are afraid about the over processing, or the cost is the major factor behind it?
Right. So shelf life. Well, what do you need the shelf life, right? So from a consumer point of view, so they are going to look at the product and they have the interest to get the product consumed immediately. So if I am going to buy a gallon of milk, I want to see maybe is it processed yesterday or last week, I think it's good. Whereas if I have that milk processed 3 months or 1 year before, I have in my mind something wrong with this milk. This is a very old milk, so something may be wrong, and those type of things. From a food science or engineering point of view, you start with a certain quality of the ingredient, and then you, through packaging and processing, you protect that quality without any changes. That milk is same as whether you purchased 3 months ago or you purchased today, because the quality doesn't change. But the consumers have this perception, right? So the commercial processor, they are interested in selling to the consumers and catering their needs. So that's where I think a lot of times the shelf life, they primarily look at things from a what they call how much time to transport from the factory to the store, and then how much time they have to have it in the consumer shelf and so on and so forth. Now, here we are getting into a different discussion. What is the best buy, what is sell by, all those things, because again that's much more subjective, because from a best buy point of view, it just says that if I buy the milk as an example, this tastes good from a quality point of view if you consume within that time from a sensorial perspective. But maybe you keep the milk for another 2 weeks, from a microbiological point of view, that milk is still good, but consumer doesn't know microbiological quality or sensory quality. They see it, then they throw that milk away. So that's kind of totally a different discussion.
Dr. Bala, I have two questions. The first one being, how do we decide whether we should use a factor of 2 or a factor of 3 for accelerated shelf life studies when it comes to monitoring the spoilage?
Right. So, a simplistic factor you can think about is, let's say like what is the contributing agent for your spoilage. So, this may be a microbe or it can be a chemical deterioration. So, once you identify that agent, then you determine the rate constant at one temperature and determine the rate constant in the second temperature. So, let us say 70 and 80, and then look at the values. So, if the values come as let us say 3 and 2, then the ratio is 1.5, then that means that factor is 1.5. Okay. So, whereas if I have value 4 and 2, then the ratio is 2, then that factor is 2.
Okay, so you are suggesting that the equation, the Q10 equation that we just saw, each time we are trying to decide on the shelf life which factor to use, so each time we will have to put that equation into, you will have to work with that equation. Is that what you are trying to suggest?
No, like I think that's one way to establish the shelf life, but you as a producer probably need to know what is the thing you are targeting, right? Is it my enzyme spoilage is my rate limiting step, or microbial kinetics is the limiting step, or some textural modification is my rate limiting step. So, once you have that knowledge, then you determine that K values, and then you calculate that value, then you can able to estimate the shelf life.
Okay. Okay.
Right, because I think it may be one for one product, a different thing for a different product.
Yeah, exactly.
So, it's kind of you have to look at that, and it's possible it may be also consumer dependent, in some cases, because consumer may reject in one part of the world, but the other part of the world the consumer may accept it. So, you have to kind of consider all those things.
Sure. This was the exact thing I was trying to understand, because I've previously worked on shelf life and I'm not applying this equation in the industry was a very big challenge because they wanted it in a specific time. And that was very difficult to achieve. So we actually, I don't know whether that was the right thing to do, but we took a factor of 2 for certain products after studying what ingredients they have and how they are being processed. So the factor of 2 was with a temperature of 45 degrees Celsius and a RH of 65%, and the factor of 3 was 65 degrees Celsius. So I'm not quite sure if that was the right approach to have, but we did conduct sensory testing as well, and that's how the accelerated shelf life took place.
Right. So, like I think again, to some extent, food designing, some of this thing, partly very scientific. On the other side, it can be art based on your past experience. So, if you are in the field for 20, 30 years, you kind of have some sense of, okay, this product going to behave this way versus the other way. Then somebody say, okay, go ahead and use the factor of 3, this will do fine, or go and use the factor of 2. They don't need to study all the details, but they can get that. And then as long as consumers support those decisions, people just follow that, right?
Right. That's exactly what happened.
Right, right. Yeah. So, you know, it's one thing we talk things in the academics, but in the industry sometime they are under pressure with the time and number of
exactly.
things. So they have to just to use some rule of thumbs type of thing.
Yeah, that's exactly what we did, and I always wondered, because I had that, you know, little bit guilt in me that I always thought, are we doing the right thing?
Right.
You know.
You know, again, it's possible if you do systematically the experimentation, your factor may be, let's say if you choose 2, your factor may be 1.9 or 2 or 2.01, so that when you choose that, it probably seems to be working fine. Even though you did not do the studies, it may be close enough so that approximation of 2 may work out good for you.
Yeah, I hope so too, but we also simultaneously conducted real-time studies.
Right.
So we tried to manage both, but it wasn't, in case of all customers, they didn't really want to spend that much money on real-time. If they got results with accelerated, they were going ahead with that.
Right, sure.
Thank you so much.
Thank you.
It just makes me feel good that, you know, I did the right thing probably.
Yeah, you know, like a lot of times you have theory, but in practice the industry always try to come up with their own version of doing things. So
Yes, yes. Thank you.
Okay, sir.
Okay.
Today we can
okay,
end here.
right, sure.
So thanks for everyone coming here. So tomorrow be present 8:45 AM.
Thank you. See you tomorrow.